Hello there, and welcome to Physics with William, where we take complex ideas from the edges of modern science and explore them slowly, carefully, and without rushing past the details that make them extraordinary. Tonight, we're turning our attention to something so small that it challenges the very structure of reality itself. Not an atom, not a particle, not even a quark. Something far beyond that. We're going to talk about what physicists call the Planck length, a number so tiny that it may represent the smallest possible distance that can exist in our universe. Before we get into equations or theories, take a moment and consider something simple. Where are you listening from right now? Maybe it's late evening where you are. Maybe it's early morning. Perhaps you're at a desk or on a couch or lying in bed. Whatever your setting, you're surrounded by space. The room has width, height, and depth. The walls are a certain distance apart. Your hands are a measurable distance from your face. Everything around you occupies space. Now imagine shrinking that space. Imagine dividing the distance between your hands in half, then in half again and again. Keep going. There's no obvious reason to stop. Mathematics allows you to divide a distance endlessly. Half, quarter, eighth, 16th, and so on, without limit. For most of human history, that seemed perfectly reasonable. Space was assumed to be continuous, smooth, infinitely divisible. But modern physics has a habit of challenging assumptions that once felt obvious. Tonight's question is deceptively simple. Is there a smallest possible distance? A fundamental limit beneath which the concept of space itself stops making sense? If you find this kind of exploration calming or thought-provoking, consider liking the video or subscribing. It helps this quiet corner of science reach others who enjoy slowing down and examining the foundations of reality. Now, let's ease into the problem. For centuries, scientists have asked what things are made of. The ancient Greeks proposed atoms as indivisible building blocks. In the 19th century, atoms became scientific reality. In the 20th century, atoms were split into protons, neutrons, and electrons. Protons and neutrons were then broken into quarks. Each time we thought we had reached something fundamental, a deeper layer appeared. So it's natural to wonder, if we keep going, will we eventually reach something that cannot be divided any further? Not just the smallest particle, but the smallest possible separation between 2 points. To understand why this question matters, we need to think carefully about what distance means. Distance is not a thing you can hold, it's not a substance. It's a relationship between two positions in space. If I say two objects are 1 meter apart, that statement refers to space itself, the arena in which objects exist. Classical physics, the physics of Isaac Newton, treated space as a smooth backdrop, an infinite stage on which events unfolded. You could measure distances as precisely as your instruments allowed, and in principle, you could always measure more precisely. There was no built-in limit. Even Einstein's theory of relativity, which revolutionized our understanding of space and time, still described space-time as a smooth geometric fabric. It could bend and curve in the presence of mass and energy, but it was continuous. You could zoom in forever without encountering any graininess. Yet when quantum mechanics entered the picture in the early 20th century, continuity began to look less secure. Quantum theory introduced the idea that certain physical quantities are not infinitely divisible. Energy, for example, comes in discrete packets called quanta. That realization came from Max Planck, the physicist whose name is attached to the Planck length. Planck was studying black-body radiation when he discovered that energy is exchanged in tiny discrete units, proportional to a constant that now bears his name, Planck's constant. That discovery marked the beginning of quantum physics. It told us that nature has built-in scales. There are minimum units of action, minimum units of energy exchange. Not everything can be sliced endlessly. This raises a natural question. If energy is quantized, could space itself also have a smallest unit? To approach that, physicists combine three fundamental constants of nature: the speed of light, which governs relativity, Planck's constant, which governs quantum mechanics, and the gravitational constant, which governs gravity. When you combine these three constants in a particular way, something remarkable happens. Out of the mathematics emerges a natural unit of length, not defined by human convention, not based on meters or inches, but determined entirely by the structure of the universe. That length is approximately 1.6 times 10 to the negative 35 meters. To put that in perspective, a meter is roughly the width of a doorway, a millimeter is 1,000th of that, a micrometer is 1/1,000,000th, a nanometer is 1/1,000,000,000th, an atom is about 1/10th of a nanometer across, a proton is about 1/quadrillionth of a meter. The Planck length is smaller than a proton by a factor of about 10 to the 20. That's a 1 followed by 20 zeros. If you enlarged a proton to the size of the observable universe, the Planck length would still be smaller than an atom in that scaled-up universe. The difference is almost beyond comprehension. Numbers that small tend to blur together, so it helps to remember that the Planck length is not just very small, it is unimaginably small. It sits at a scale where our current physical theories begin to conflict with one another. Here's why that matters. Quantum mechanics governs the behavior of particles at extremely small scales. General relativity governs the behavior of gravity and large-scale structures like stars and galaxies. Both theories are extraordinarily successful in their own domains, but when you push down to distances comparable to the Planck length, both quantum effects and gravitational effects become equally important. At that scale, spacetime itself is subject to quantum uncertainty. Normally, when we talk about uncertainty in quantum mechanics, we mean uncertainty in the position or momentum of particles. But near the Planck scale, the geometry of spacetime becomes uncertain. It's no longer a smooth, stable backdrop. It fluctuates. If you attempt to measure a position with greater and greater precision, you must use higher and higher energy. That's because shorter wavelengths of light correspond to higher energy photons. To probe smaller distances, you need shorter wavelengths. But as the energy increases, gravity also becomes stronger. At some point, concentrating enough energy into a small region would create a microscopic black hole. That threshold occurs roughly at the Planck length. In other words, if you try to measure distances smaller than the Planck length, the act of measurement would distort spacetime so violently that the region would collapse into a black hole, hiding the very thing you were trying to observe. This suggests that the Planck length may not just be a convenient unit. It may represent a fundamental limit to meaningful measurement, and that idea changes how we think about reality. In everyday life, we assume that space is smooth. If you draw a straight line on a piece of paper, you can zoom in as much as you like and it remains continuous. But if space has a smallest possible scale, then at some level it might resemble something more like a grid or network. Not necessarily in a literal pixelated sense, but in the sense that there is a minimum unit beyond which subdivision loses physical meaning. This doesn't mean space is made of tiny cubes or discrete blocks in the way a digital image is made of pixels. The true structure, if there is one, would be far more subtle. Some theories, like loop quantum gravity, suggest that space is woven from tiny loops at the Planck scale. Others, like string theory, imply that particles themselves are tiny vibrating strings, whose characteristic size is near the Planck length. What all of these ideas share is a recognition that the Planck scale marks a boundary. On one side, our familiar theories function reliably. On the other side, those theories break down. When physicists talk about new physics, they often mean physics that becomes relevant at extreme energies or tiny distances. The Planck length defines an energy scale as well, the Planck energy, which is far beyond anything our current particle accelerators can reach. The Large Hadron Collider, the most powerful machine of its kind, operates at energies trillions of times smaller than the Planck energy. That gap is enormous. It means that experimentally probing the Planck length directly is currently impossible. We cannot build an instrument capable of resolving such distances. The energies required would dwarf anything humanity has ever produced. So the Planck length occupies an unusual position in physics. It is theoretically significant but experimentally inaccessible. Yet its significance runs deep. It tells us that the constants of nature, the speed of light, Planck's constant, and gravity define a natural scale where the classical picture of spacetime ceases to apply. The more you think about that, the more profound it becomes. We live our lives in a world that feels continuous. We measure rooms in meters, roads in kilometers, planetary distances in millions of kilometers. None of that hints at a smallest scale. And yet, according to our best theories, there may be a built-in limit to how finely space can be divided. If that's true, then space is not infinitely divisible. It has a kind of atomic structure, not made of matter, but of geometry itself. And that leads us naturally to a deeper exploration. Because to understand why the Planck length takes the value it does, and why those three constants combine to produce it, we need to look more closely at how physicists discovered that nature even has fundamental scales in the first place, and how the quantum revolution forced a reconsideration of what can and cannot be divided without limit. When we talk about something being small, we usually mean smaller than what we're used to seeing. A grain of sand is small compared to a pebble. A bacterium is small compared to a grain of sand. An atom is small compared to a bacterium, but in physics the word small has a more precise meaning. It refers to measurable scales, each smaller than the last, arranged not by intuition but by experiment. To understand what makes the Planck length extraordinary, we need to build a sense of scale step by step. That means starting at sizes that feel familiar, and then moving steadily downward, until the numbers stop feeling intuitive at all. Begin with something visible. A human hair is roughly 70 micrometers in diameter. A micrometer is 1/1,000,000th of a meter. Already we're dealing with numbers far smaller than everyday experience, but still within reach of a decent microscope. Bacteria are typically a few micrometers across. Human cells are about 10 to 30 micrometers wide. With magnification, these are manageable sizes. Now shrink another 1,000 times. 1 nanometer is 1/1000,000th of a meter. DNA is about 2 nanometers wide. A typical protein molecule may span a few nanometers. At this scale, chemistry governs behavior. Molecules bond, break, and rearrange. But molecules themselves are made of smaller components. An atom measures roughly 1/10th of a nanometer, or about 0.1 nanometers, that's 10 to the negative 10 meters. If you lined up 10 million atoms side by side, they would stretch about 1 millimeter. Atoms are the building blocks of matter in the chemical sense. They define elements, structure, and material properties. For a long time, atoms were thought to be indivisible. The word itself comes from the Greek atomos, meaning uncuttable. That assumption held until the late 19th and early 20th centuries, when experiments began to show that atoms had an internal structure. In 1897, J.J. Thomson discovered the electron. This was the first indication that atoms were not fundamental. They contained smaller charged particles. Later, Ernest Rutherford's gold foil experiment revealed that most of the atom's mass is concentrated in a tiny central nucleus. The nucleus itself is extraordinarily small compared to the atom. If the atom were the size of a football stadium, the nucleus would be about the size of a pea at the centre. The rest would be mostly empty space occupied by a cloud of electrons. A typical atomic nucleus has a radius on the order of 10 to the negative 15th meters. That's 1 femtometer. Compared to the size of the entire atom, the nucleus is about 100,000 times smaller. Within the nucleus are protons and neutrons. For a while, these particles were considered fundamental. But mid-20th century experiments in particle accelerators revealed that protons and neutrons are also composite. They're made of even smaller entities called quarks. Quarks have never been observed in isolation. They are permanently confined within protons and neutrons due to the strong nuclear force. Still, high-energy scattering experiments provide clear evidence of their existence. Protons and neutrons are each made of 3 valence quarks, held together by particles called gluons. So how small are quarks? Current experimental limits suggest that quarks behave like point particles down to distances of at least 10 to the negative 19 meters. That's 1/10,000th the size of a proton. At that scale, experiments have not detected any internal structure. As far as we can tell, quarks are fundamental. But notice the language carefully. We say, as far as we can tell. That qualification is important. Physics does not claim absolute finality. It reports what experiments can resolve. If future experiments probe smaller distances and find structure within quarks, our understanding will shift again. To probe smaller distances, physicists use higher energy collisions. This is not arbitrary. The relationship between energy and resolution comes from quantum mechanics. According to the de Broglie relation, the wavelength of a particle is inversely proportional to its momentum. Shorter wavelengths allow finer resolution. Higher momentum requires higher energy. In practical terms, if you want to see smaller things, you need more energetic probes. Particle accelerators are essentially microscopes. Instead of using visible light, they use high-energy particles. The more energy you pack into the collision, the smaller the structures you can investigate. The Large Hadron Collider accelerates protons to energies of several tera-electron volts. At these energies, we can probe down to roughly 10 to the negative 19 meters. That's about 16 orders of magnitude smaller than an atom. And yet, even this scale is unimaginably larger than the Planck length. The Planck length is about 1.6 times 10 to the negative 35 meters. Compare that to 10 to the negative 19 meters. That's a difference of 16 additional orders of magnitude. In other words, the gap between current experimental reach and the Planck scale is about the same as the gap between the size of a proton and the size of a human. When you line up the hierarchy, human scale, cellular scale, molecular scale, atomic scale, nuclear scale, quark scale, each step represents dramatic increases in precision and energy. But the jump from quarks to the Planck length is not just another step. It's a chasm. It's also worth considering that at each stage of discovery, the concept of smallest has shifted. Atoms were once thought indivisible. Then nuclei were considered fundamental. Then protons and neutrons. Now quarks and leptons are treated as elementary particles within the Standard Model. The Standard Model of particle physics currently describes 12 fundamental fermions, 6 quarks and 6 leptons, along with gauge bosons that mediate forces. Within this framework, particles are treated as point-like down to experimentally accessible scales. But the Standard Model does not include gravity in a quantum framework, and it is precisely gravity that becomes unavoidable when we approach the Planck length. To see why gravity matters at such small scales, consider how weak gravity normally is. The gravitational attraction between two electrons is negligible compared to their electromagnetic repulsion. At atomic scales, gravity can be ignored. However, as you push towards smaller and smaller distances, the energy required to probe those scales increases dramatically. Energy, according to Einstein's equation E equals mc squared, is equivalent to mass. Concentrated enough energy in a small enough region increases gravitational effects. Eventually, if you compress enough energy into a sufficiently tiny space, the gravitational field becomes so strong that it forms a black hole. This threshold occurs near the Planck length. So while gravity is irrelevant at atomic and nuclear scales, it cannot be ignored at the Planck scale. That's one reason the Planck length stands apart from all other small distances we've discussed. It's not just another smaller layer of structure. It marks the point where our separate theories, quantum mechanics and general relativity, must both apply simultaneously. At atomic scales, quantum mechanics dominates. At astronomical scales, gravity dominates. At the Planck scale, neither can be ignored. There is another important distinction between quarks and the Planck length. Quarks are particles. The Planck length is not a particle. It is a unit of length derived from fundamental constants. It represents a limit of measurement, not a constituent of matter. When we discovered quarks, we found smaller pieces of matter. When physicists discuss the Planck length, they're not necessarily proposing a smaller particle. They're proposing a smallest meaningful interval of space itself. That's a profound shift in perspective. Up to the level of quarks, the question, how small is small, refers to smaller pieces of stuff, smaller building blocks, smaller objects. At the Planck scale, the question becomes, how small can distance be before the concept of distance stops behaving normally? This distinction matters because dividing matter and dividing space are not identical problems. You can imagine splitting a particle into smaller parts, but can you split space infinitely? In classical mathematics, yes. In physical reality, perhaps not. Some approaches to quantum gravity suggest that space is quantized in units related to the Planck length. Loop quantum gravity, for example, predicts discrete spectra for areas and volumes. In such models, space itself has a kind of atomic structure, though not in the ordinary sense. Other theories, such as string theory, do not explicitly quantize space in the same way, but still treat the Planck scale as fundamental. Strings are thought to have a characteristic size near this scale. Below that, the idea of point-like particles breaks down. Even without committing to a specific theory, most physicists agree on one thing. The Planck length defines a boundary beyond which our current mathematical descriptions lose predictive reliability. When you zoom from a meter down to a micrometer, nothing strange happens to space itself. When you zoom from a micrometer to a nanometer, the geometry remains smooth. Even at nuclear scales, space behaves classically. But near 10 to the negative 35 meters, the smooth continuum picture likely fails. One way to visualize this, without resorting to metaphor, is to consider measurement uncertainty. To localize an event within a region smaller than the Planck length would require energy so concentrated that the uncertainty in spacetime curvature becomes comparable to the scale being measured. At that point, geometry fluctuates. The result is that distance becomes a probabilistic concept rather than a fixed background quantity. The progression from atoms to quarks tells a story of smaller and smaller components. But the progression toward the Planck length tells a different story, one about the limits of description itself. It's also useful to notice that each stage of smaller scale required new theoretical frameworks. Classical mechanics could not explain atomic stability. Quantum mechanics was required. Quantum mechanics alone could not explain nuclear binding. Quantum chromodynamics was required. And neither quantum field theory nor general relativity can independently describe the Planck regime. That is why the Planck length occupies such a central place in modern theoretical physics. It represents not just a tiny number, but a signal that something fundamental changes there. In summary, when we ask how small is small, we're not just asking about particles. We're tracing the boundary between known physics and unknown physics. From visible objects down to atoms, from atoms to nuclei, from nuclei to quarks, each step has revealed deeper structure. But beyond quarks lies a domain where the structure of spacetime itself may no longer be smooth or continuous. And understanding why that happens requires stepping back to examine how the quantum revolution began in the first place, and why Max Planck's constant became the key to identifying a natural scale in the universe. By the end of the 19th century, physics appeared to be nearly complete. Newton's laws described motion. Maxwell's equations unified electricity and magnetism. Thermodynamics explained heat and energy. Many prominent scientists believed that only minor refinements remained. The structure of reality seemed orderly, predictable, and continuous. And yet, beneath that confidence, certain experimental results refused to fit. One of the most troubling problems involved something deceptively ordinary: glowing objects. When a piece of metal is heated, it begins to emit light. First red, then orange, then white, as the temperature increases. This behavior was well documented, but the theoretical explanation proved difficult. Physicists tried to calculate the spectrum of light emitted by a so-called black body, an idealized object that absorbs and emits radiation perfectly. Classical physics predicted that as the wavelength of light became shorter, the intensity of radiation should increase without limit. This implied that hot objects would emit infinite energy at very short wavelengths. That prediction was clearly wrong. It became known as the ultraviolet catastrophe. The problem was not subtle. The mathematics was elegant, but the result was absurd. Something in the classical understanding of energy distribution was incomplete. In 1900, Max Planck approached the issue from a different angle. Planck was not trying to revolutionize physics. He was trying to fix a specific calculation to make the equations match experimental data. He introduced a mathematical assumption that energy is not exchanged continuously. Instead, energy could only be emitted or absorbed in discrete amounts proportional to the frequency of radiation. The proportionality constant he introduced is now called Planck's constant. At first, Planck considered this assumption a formal trick, a computational device. He did not initially claim that energy itself was fundamentally discrete. But the equations worked. The blackbody spectrum matched observations perfectly. What Planck had done, perhaps reluctantly, was introduce the idea that nature has built-in units of action. Energy does not vary smoothly in all contexts. It comes in packets. This marked the beginning of quantum thinking. 5 years later, Albert Einstein extended the idea further. In 1905, he proposed that light itself is quantized. Instead of being purely a continuous wave, light could behave as discrete particles, later called photons. This proposal explained the photoelectric effect, where light striking a metal surface ejects electrons. Classical wave theory could not account for certain features of this effect. For example, increasing the intensity of low-frequency light did not eject electrons, but increasing the frequency did, even at low intensity. Einstein's explanation treated light energy as concentrated in individual quanta. Each photon carried energy proportional to its frequency. This was a decisive break from classical thinking. The next major step came with Niels Bohr's model of the hydrogen atom in 1913. Classical electromagnetism predicted that electrons orbiting a nucleus should continuously radiate energy and spiral inward. Atoms should collapse, yet atoms are stable. Bohr proposed that electrons occupy discrete energy levels. They can jump between these levels by absorbing or emitting specific quanta of energy. The allowed orbits were quantized. Although Bohr's model was later replaced by more sophisticated formulations, it reinforced the emerging pattern. At microscopic scales, physical quantities are not continuous. Over the following decades, quantum mechanics was formalized through the work of Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and others. The mathematical framework they developed was unlike anything in classical physics. One of the central features of quantum mechanics is the uncertainty principle. Heisenberg showed that certain pairs of physical quantities, such as position and momentum, cannot both be known with arbitrary precision. The more precisely one is measured, the less precisely the other can be determined. This uncertainty is not due to technological limitations. It is a fundamental property of nature. In classical physics, a particle has a definite position and velocity at all times. In quantum mechanics, particles are described by wave functions which encode probabilities. Measurement does not simply reveal pre-existing values. It interacts with the system in a way that affects outcomes. These developments change the meaning of small. At atomic scales, particles do not behave like tiny billiard balls. They exhibit wave-particle duality. They interfere with themselves. They tunnel through barriers. Their properties are inherently probabilistic. This shift in thinking had profound implications for our understanding of measurement and scale. In classical reasoning, smaller distances simply require better instruments. There is no conceptual barrier to infinite divisibility. In quantum mechanics, however, probing smaller distances requires higher energy. And because energy and wavelength are linked, Resolving finer structure demands shorter wavelengths and therefore greater momentum. But increasing energy introduces complications. High-energy probes do not passively observe, they interact strongly. At sufficiently small scales, the act of measurement alters the system dramatically. The concept of quantization extends beyond energy levels in atoms. Fields themselves are quantized. In quantum field theory, particles are excitations of underlying fields. The electromagnetic field, for example, gives rise to photons when excited. The electron field gives rise to electrons. The vacuum is no longer empty. It is filled with fluctuating fields. Virtual particles constantly appear and disappear within the limits set by the uncertainty principle. This picture of reality is fundamentally different from the smooth, deterministic universe of classical mechanics. And yet, quantum mechanics does not by itself imply a smallest possible distance. The equations of quantum field theory are still formulated on a continuous spacetime background. They assume that space and time can be divided arbitrarily finely. This creates tension. On one hand, quantum theory introduces discreteness in energy and action. On the other hand, it still relies on a continuous geometry. Meanwhile, general relativity describes gravity as curvature of spacetime itself. That curvature is smooth and continuous as well. When physicists attempt to combine these frameworks, difficulties arise. Calculations of quantum gravitational effects produce infinities that cannot be removed using standard techniques. The mathematics breaks down at extremely small scales. The Planck length emerges from this intersection. Planck's constant governs the strength of quantum effects. The speed of light governs relativity. The gravitational constant governs gravity. Combining them yields a length scale at which quantum fluctuations of spacetime become significant. The birth of quantum thinking was not about discovering something small in the ordinary sense. It was about discovering limits. Limits on energy exchange, limits on precision, limits on predictability. Before quantum mechanics, energy was thought to vary continuously. After Planck, energy had a minimum unit. Before Heisenberg, measurement precision was thought to be limited only by instrument quality. After the uncertainty principle, precision itself had a fundamental boundary. This progression naturally leads to the question of whether distance might also have a limit. If energy is quantized, and if probing smaller regions requires higher energy, and if high energy curves spacetime through gravity, then there may be a scale at which further subdivision is physically meaningless. It is important to recognize that Planck himself did not propose a smallest distance in 1900. The concept of the Planck length came later, when physicists realized that his constant could be combined with others to produce natural units. Planck defined natural units of length, time, mass, and energy by setting fundamental constants equal to 1 in appropriate combinations. These units are not arbitrary. They do not depend on human conventions like meters or seconds. They arise directly from the structure of physical law. The Planck length is one such unit. The quantum revolution therefore did more than explain atomic spectra. It introduced a way of thinking in which nature contains built-in scales. It shifted the assumption of continuity to one of discreteness in certain contexts. As physicists pushed deeper into high-energy regimes throughout the 20th century, this framework proved extraordinarily successful. Quantum electrodynamics, quantum chromodynamics, and the electroweak theory all rely on quantized fields and interactions. Yet gravity remains outside this quantum description. The incompatibility between general relativity and quantum mechanics becomes unavoidable at extremely small distances. That threshold is set by the Planck scale. So when we speak of the birth of quantum thinking, we are describing more than a historical episode. We are describing a conceptual transformation. The idea that the universe has fundamental units, that measurement has intrinsic limits, and that classical continuity cannot be assumed at all scales. This intellectual shift laid the groundwork for identifying a smallest meaningful length. To understand how that smallest length is calculated and why it takes the specific value it does, we now need to examine Max Planck's constant more closely and see how combining it with the constants governing light and gravity leads directly to the Planck length itself. At the turn of the 20th century, Max Planck was not trying to overturn centuries of physics. He was a careful, methodical theorist working within the established framework of thermodynamics and electromagnetism. His goal was modest: to understand how heated objects emit radiation. Yet in solving that narrow problem, he introduced a constant that would redefine the foundations of physical law. To appreciate what Planck did, it helps to understand the scientific environment he worked in. Classical physics at the time treated energy as continuous. If a system could have 5 joules of energy, it could just as easily have 5.0001 joules or 5.000001 joules. There was no smallest step. Energy was assumed to vary smoothly, like the height of water in a glass. Planck was studying blackbody radiation, the distribution of light emitted by an object in thermal equilibrium. Experimental measurements were precise and reliable. The problem was theoretical. Existing equations derived from classical electromagnetism and statistical mechanics failed to match observed data at short wavelengths. The predicted spectrum rose without bound as wavelength decreased. Real objects did not behave that way. Instead, the emitted intensity peaked at a certain wavelength and then dropped off sharply at higher frequencies. Planck attempted various mathematical strategies to correct the discrepancy. Eventually, in October of 1900, he introduced an assumption that energy exchange between matter and radiation occurs in discrete amounts proportional to frequency. He proposed that the energy of an oscillator could only take values equal to integer multiples of a fundamental quantity, E equals h times f, where f is frequency and h is a new constant. This constant, now called Planck's constant, has the value approximately 6.626 times 10 to the power of minus 34 joule seconds. The number itself is small, but its implications are not. Planck's constant sets the scale at which quantum effects become significant. Whenever physical processes involve action, the product of energy and time, comparable to h, classical descriptions fail and quantum behavior emerges. Initially, Planck viewed his quantization hypothesis as a mathematical device rather than a statement about reality. He did not claim that oscillators physically jumped between discrete energies. He introduced the assumption reluctantly, describing it as an act of desperation to make the equations match experiment. Yet, the match was exact. Einstein soon recognized that Planck's idea had deeper meaning. In explaining the photoelectric effect, Einstein treated light itself as composed of discrete quanta, each carrying energy equal to h times f. This interpretation earned him the Nobel Prize in 1921. Over time, Planck's constant became central to quantum mechanics. It appears in the Schrödinger equation, which governs the evolution of quantum systems. It appears in Heisenberg's uncertainty principle, which can be written in terms of the reduced Planck constant, h bar, equal to h divided by 2 pi. The uncertainty principle states that the product of uncertainties in position and momentum must be greater than or equal to h bar divided by 2. This is not a limitation of measurement tools. It reflects the intrinsic structure of quantum states. Planck's constant therefore defines a boundary between classical and quantum regimes. When the characteristic action of a system is much larger than h, quantum effects are negligible. When it is comparable to h, quantum behavior dominates. To see this more concretely, consider angular momentum. In classical physics, angular momentum can take any value. In quantum mechanics, angular momentum is quantized in units of h bar. Electrons in atoms do not orbit with arbitrary angular momentum. They occupy discrete states determined by integer multiples of this fundamental unit. Similarly, energy levels in atoms are quantized. Electrons can only occupy specific energy states separated by fixed intervals, determined by Planck's constant and other physical parameters. Transitions between levels involve emission or absorption of photons whose energies are precisely defined. Planck's constant also governs wave-particle duality. The de Broglie wavelength of a particle is given by lambda equals h divided by p, where p is momentum. This relation shows that every particle has an associated wavelength, though for macroscopic objects it is so small as to be undetectable. For example, a baseball moving at typical speeds has a de Broglie wavelength far smaller than atomic dimensions. Quantum effects are therefore negligible at everyday scales. But for electrons, whose momenta are small enough that h divided by p is comparable to atomic sizes, wave behavior becomes evident. In this way, Planck's constant acts as a conversion factor between classical and quantum descriptions. It is important to recognize that h is not derived from deeper theory within quantum mechanics. It is a fundamental constant measured experimentally. Its numerical value is woven into the fabric of physical law. Planck himself went further. In 1899, even before fully developing quantum theory, he introduced the idea of natural units. By combining fundamental constants, the speed of light c, the gravitational constant g, and his newly introduced constant h, he defined units of length, time, mass, and temperature that depend only on universal properties. These are now called Planck units. The Planck length is constructed from h, g, and c in a specific combination that yields dimensions of length. Using the reduced Planck constant h-bar, the formula is Lp equals the square root of hg over c cubed. When evaluated numerically, this gives approximately 1.6 times 10 to the power of minus 35 meters. What is striking about this formula is that it links quantum mechanics through h-bar, relativity through c, and gravity through g. The Planck length emerges from the intersection of these three domains. Planck did not interpret this length as a smallest possible distance in the way modern physicists sometimes do. However, the existence of a natural length scale suggested that nature contains fundamental boundaries beyond which existing theories might fail. To understand why these three constants combine to produce such an extraordinarily small number, consider their roles individually. The speed of light c sets the maximum speed at which information can travel. It links space and time in relativity, converting between units of length and duration. The gravitational constant g measures the strength of gravity. It determines how mass curves space-time. Planck's constant h-bar measures the scale of quantum fluctuations. It sets the size of quantum effects relative to classical expectations. When combined, they define a scale at which quantum fluctuations of the gravitational field itself become significant. At ordinary energies, gravity is weak compared to other forces. Quantum fluctuations in space-time curvature are negligible. But as energy increases and distances shrink, gravitational effects grow stronger. At sufficiently small scales, quantum uncertainty in geometry becomes unavoidable. The Planck length marks the approximate threshold where this happens. To illustrate this point, consider a thought experiment. Suppose you attempt to localize a particle within a region of size L. According to quantum mechanics, the uncertainty in momentum increases as L decreases. Greater momentum uncertainty implies higher energy uncertainty. If you attempt to confine a particle within a region smaller than the Planck length, the energy required becomes so large that, according to general relativity, the region would collapse into a black hole. This argument suggests that attempting to probe distances smaller than Lp is physically self-defeating. The energy concentration would distort space-time itself. In this sense, the Planck length is not merely small, it represents a conceptual boundary. Below this scale, classical geometry cannot be assumed to hold. Planck's constant therefore does more than define quantum behavior in atoms. Through its role in natural units, It signals the scale at which our current theoretical frameworks must be unified. The remarkable aspect of Planck's discovery is that it arose from a practical attempt to match experimental data. He was not searching for the ultimate scale of reality. He was solving a radiation problem, yet the constant he introduced became central to every quantum equation that followed. Without it, the Schrödinger equation would reduce to classical mechanics. Without it, the uncertainty principle would vanish. Without it, matter would collapse under electromagnetic forces as classical physics predicted unstable atoms. Planck's constant ensures atomic stability. It governs chemical bonding. It defines the structure of solids, the emission spectra of stars, and the behavior of semiconductors. And when combined with gravity and relativity, it defines the smallest meaningful length scale in nature. It is rare in science for a single constant to reshape entire domains of inquiry. Planck's constant did exactly that. It transformed energy from a continuous variable into a quantized property. It introduced intrinsic limits to measurement, and it laid the groundwork for recognizing that space and time themselves may possess a fundamental scale. Understanding how that scale is defined numerically and why it takes the specific value it does requires looking more closely at the mathematical construction of the Planck length itself and examining how these constants combine to produce a distance so small that it challenges the continuity of space-time. At this point, we have traced the path from visible objects down to atoms, from atoms to quarks, and from classical continuity to quantum discreteness. We have seen how Planck's constant introduced a fundamental scale into physics, and how combining it with the constants governing gravity and relativity produces a natural unit of length. Now it's time to state clearly what the Planck length actually is and what it is not. The Planck length is defined as Lp equals the square root of hg over c cubed. Here, h is the reduced Planck constant, g is the gravitational constant, and c is the speed of light. When you substitute the numerical values of these constants, you obtain approximately 1.616 times 10 to the power of minus 35 meters. That number is extraordinarily small. But the important point is not just its size, it is how it arises. Unlike the meter, which is defined by human convention, or the kilometer, which is simply a multiple of that convention, the Planck length does not depend on arbitrary choices. It is constructed entirely from fundamental constants of nature. If an advanced civilization in another galaxy measured h bar, g and c, they would calculate the same Planck length. This makes it a natural unit. To understand what this length represents, consider the dimensions involved. Planck's constant has units of action, which is energy multiplied by time. The gravitational constant relates mass to curvature of space-time. The speed of light relates space and time. When these are combined in the specific arrangement square root of hg over c cubed, the resulting dimensions reduce to length. This is not an accident. It reflects the interplay between quantum mechanics, gravity, and relativity. Each constant alone governs a distinct domain. H bar governs quantum uncertainty and quantization. G governs gravitational attraction and curvature. C governs the structure of space-time and the maximum speed of causal influence. The Planck length is the scale at which all three become equally important. At larger distances, gravity is typically negligible compared to electromagnetic and nuclear forces. At atomic scales, quantum mechanics dominates while gravity can be ignored. At astronomical scales, general relativity dominates while quantum fluctuations are insignificant. But at distances on the order of 10 to the power of minus 35 meters, these regimes overlap. Quantum fluctuations in energy are strong enough to significantly curve space-time. Gravity can no longer be treated as weak, and classical descriptions of geometry break down. It is crucial to clarify what the Planck length does not mean. It does not necessarily imply that space is made of tiny cubes of that size. it does not automatically mean that there is a literal grid underlying reality. The Planck length is a scale derived from theory. Whether space is discrete at that scale depends on which theory of quantum gravity is correct. What most physicists agree on is that below this scale, our current mathematical descriptions cannot be trusted. To see why, consider a thought experiment involving measurement. Suppose you want to determine the position of a particle with extremely high precision. According to quantum mechanics, the uncertainty in position delta x and momentum delta p are related by delta x times delta p greater than or equal to h bar over 2. To reduce delta x, you must increase delta p. But momentum relates to energy. High momentum implies high energy. If you attempt to confine a particle within a region smaller than Lp, the required energy becomes so large that, according to general relativity, it would significantly curve space-time. In fact, beyond a certain threshold, concentrating that much energy into such a small region would form a microscopic black hole. The Schwarzschild radius associated with that energy would exceed the region you are trying to probe. The region would be hidden behind an event horizon. This suggests a fundamental limit to localization. The Planck length is approximately the scale at which the Compton wavelength of a particle, a quantum mechanical concept, becomes comparable to its Schwarzschild radius, a gravitational concept. When these two lengths coincide, neither quantum mechanics nor general relativity alone provides a complete description. Another way to interpret the Planck length is through the concept of quantum foam. At macroscopic scales, space-time appears smooth, but at extremely small scales, quantum fluctuations may cause it to fluctuate violently. Tiny distortions in geometry may appear and disappear rapidly. These fluctuations would be negligible at everyday distances, but near Lp they become significant. The term quantum foam, introduced by John Wheeler, describes this idea. It suggests that space-time at the Planck scale is not smooth but turbulent. However, this is a heuristic picture. A full theory of quantum gravity is required to describe it precisely, and such a theory remains incomplete. The Planck length also defines related units. The Planck time is the time it takes light to travel one Planck length. Tp equals Lp over c. This is about 5.39 times 10 to the power of minus 44 seconds. The Planck mass is mp equals the square root of hc over g. This is about 2.18 times 10 to the minus 8 kilograms. Unlike the Planck length, the Planck mass is surprisingly large by particle physics standards. It is about 22 micrograms, enormous compared to subatomic particles. The Planck energy associated with this mass is around 10 to the power of 19 giga-electronvolts, far beyond current accelerator capabilities. These units are interconnected. The Planck length, time, mass, and energy define a regime where quantum gravity effects dominate. Importantly, the Planck length is not directly measurable with current technology. The highest energies achieved in particle accelerators correspond to length scales many orders of magnitude larger. Even cosmic rays, which carry enormous energies compared to laboratory experiments, fall far short of Planck energy. This experimental inaccessibility means that our understanding of the Planck scale is theoretical. It arises from extrapolating known laws into regimes where they may not fully apply. Still, the consistency of the Planck unit construction is compelling. Whenever you combine h, g, and c, you obtain scales that appear repeatedly in discussions of extreme physics, black hole evaporation, early universe cosmology, quantum gravity models. For example, during the first 10 to the power of minus 43 seconds after the Big Bang, roughly 1 Planck time, the universe would have been at Planck temperature and Planck density. Classical descriptions of space-time cannot be extended beyond that epoch without invoking quantum gravity. In black hole physics, the entropy of a black hole is proportional to the area of its event horizon measured in units of the Planck length squared. This suggests that Planck scale geometry may play a role in the fundamental accounting of information. These recurring appearances reinforce the idea that LP is not arbitrary. Yet the Planck length is not necessarily the smallest distance that can exist in a simple mechanical sense. Some theoretical frameworks suggest that space may be discrete at this scale. Others suggest that space remains continuous but becomes dominated by quantum gravitational fluctuations. The phrase "smallest distance that can exist" therefore needs careful interpretation. It may be more accurate to say that the Planck length is the smallest distance at which our current understanding of spacetime remains meaningful. Below this scale, the concept of classical distance may lose operational definition. In physics, meaningful quantities are those that can, at least in principle, be measured. If measuring a distance smaller than ELP requires energy that destroys the region being measured, then such distances may lack physical meaning. This is similar to how the uncertainty principle limits simultaneous precision of position and momentum. It does not forbid values, it limits measurability. In summary, the Planck length is a natural unit derived from the fundamental constants governing quantum mechanics, gravity and relativity. It marks the scale where these domains converge. It signals the breakdown of classical geometry. It defines the regime of quantum gravity. Its numerical value is extraordinarily small, far beyond direct experimental reach, yet its theoretical significance is immense. Understanding just how tiny this scale is, and how it compares quantitatively to familiar distances, requires examining the magnitude of 10 to the power of minus 35 meters in more concrete terms, and appreciating the extraordinary gap between everyday scales and the Planck regime. When people first hear the number 1.6 times 10 to the power of minus 35 meters, the reaction is usually the same. It sounds abstract, it sounds symbolic, it sounds like one of those numbers that appears in physics simply because the mathematics demands it. But the extreme smallness of the Planck length is not arbitrary. It is the direct consequence of how weak gravity is compared to the other fundamental forces, and how the constants of nature combine numerically. To understand why the Planck length is so incredibly tiny, we need to look carefully at the constants that define it. The reduced Planck constant h bar, the gravitational constant g, and the speed of light c. The formula again is Lp equals the square root of hg over c cubed. Each of these constants carries a specific physical meaning and a specific numerical value. Start with h. The reduced Planck constant is approximately 1.055 times 10 to the power of minus 34 joule seconds. This number sets the scale of quantum effects. It is already very small in everyday units, but in the formula for Lp, h bar appears multiplied by g and divided by c cubed, and then the square root is taken. Now consider g, the gravitational constant. Its value is approximately 6.674 times 10 to the power of minus 11 in SI units. Compared to constants associated with the electromagnetism or nuclear forces, g is extraordinarily small. Gravity is by far the weakest of the four fundamental interactions. The speed of light c, by contrast, is large, approximately 3 times 10 to the 8th power meters per second. And in the formula, c appears cubed in the denominator, so the Planck length involves multiplying two very small numbers, dividing by a very large number cubed, and then taking the square root. The combined effect drives the result to an extreme scale, but beyond the arithmetic, there is physical meaning behind this smallness. Gravity is weak. That statement may seem obvious, but its implications are often underestimated. The gravitational attraction between two protons is roughly 10 to the power of 36 times weaker than their electromagnetic repulsion. At atomic and subatomic scales, gravity is effectively irrelevant. It does not influence chemical bonding or nuclear structure in any measurable way. Because gravity is so weak, enormous amounts of energy are required before gravitational effects become comparable to quantum effects at small distances. To see this more clearly, consider the Planck mass, defined as mp equals the square root of hc over g. This mass is about 2.18 times 10 to the power of minus 8 kilograms. In everyday terms, that is tiny, a few micrograms. But in particle physics terms, it is enormous. A proton has a mass of about 10 to the power of minus 27 kilograms. The Planck mass is about 10 to the power of 19 times heavier than a proton. That enormous difference reflects how weak gravity is. To make gravitational interactions comparable in strength to other forces at microscopic scales, you need a mass scale that is extraordinarily high in particle terms. Now connect this back to length. The Planck length is roughly the Compton wavelength of a particle with Planck mass. It is also roughly the Schwarzschild radius of a mass equal to the Planck mass. In other words, the Planck length is the scale at which the quantum wavelength of a particle and the gravitational radius associated with its energy become comparable. Because gravity is weak, the mass required to make these two quantities equal is very large by particle standards. And because that mass is large, the corresponding wavelength, inversely proportional to mass, is very small. This is why LP is so tiny. Another way to approach this is to consider how energy relates to spatial resolution. To probe a distance L, you need particles with wavelength on the order of L. Shorter wavelengths require higher momentum. Higher momentum implies higher energy. As L becomes extremely small, the required energy increases dramatically. At distances near the Planck length, the required energy becomes so large that its gravitational effect cannot be ignored. Concentrating that much energy into such a tiny region would significantly curve space-time. But because gravity is weak at ordinary energies, you must reach extraordinarily high energy densities before gravitational curvature becomes dominant. That requirement pushes the corresponding length scale down to extremely small values. If gravity was stronger, if g were larger, the Planck length would be larger. If g were 10 to the power of 36 times bigger, gravitational effects would compete with electromagnetism at atomic scales, and the Planck length would be closer to nuclear dimensions. But in our universe, g is small. As a result, the Planck length is pushed far below nuclear scales. It is helpful to compare orders of magnitude systematically. A human is about 1 meter tall, a cell is about 10 to the power of minus 5 meters, a molecule is about 10 to the power of minus 9 meters, an atom is about 10 to the power of minus 10 meters, a nucleus is about 10 to the power of minus 15 meters. Experimental limits place quark sizes below about 10 to the power of minus 19 meters. The Planck length is 10 to the power of minus 35 meters. Notice that the gap between the nucleus and the Planck length is 20 orders of magnitude. That is not a minor extension of known scales. It is an enormous conceptual leap. Even if you imagine shrinking a proton to the size of a galaxy, the Planck length would still be far smaller than an atom in that scaled universe. This scale difference illustrates how deeply separated gravity and quantum mechanics are in practical terms. We experience quantum effects at atomic scales. We experience gravitational effects at astronomical scales. The region where they overlap lies far beyond experimental reach. The smallness of LP also reflects the fact that h-bar itself is small in SI units. In natural units often used in theoretical physics, where c equals 1 and h-bar equals 1, the Planck length is determined entirely by g. In that framework, the smallness of LP arises from the smallness of g. Physicists sometimes refer to the hierarchy problem, which addresses why gravity is so much weaker than the other fundamental forces. This weakness is directly responsible for the tiny Planck length. If gravity were comparable in strength to electromagnetism at particle scales, the Planck length would not be so remote from everyday physics. Quantum gravity effects would be observable in laboratories. Instead, the weakness of gravity isolates the Planck regime far beyond current technological capabilities. There is also a dimensional perspective to consider. The Planck length involves c cubed in the denominator. Because c is large, cubing it amplifies its magnitude dramatically. Dividing by c cubed reduces the value under the square root significantly. Taking the square root then produces an extremely small result. This reflects how strongly relativity constrains interactions at high energies. The speed of light sets a scale for converting between space and time. Its large value ensures that relativistic corrections become important only at very high velocities and energies. Combine that with the weakness of gravity and the smallness of h-bar, and the outcome is inevitable. A length scale far removed from anything we can directly observe. It is worth emphasizing that the Planck length is not small in the same way a bacterium is small. It is small in a fundamental sense. It represents the scale at which our separate theoretical frameworks converge. Because gravity is so weak, the convergence happens only at extraordinarily high energies and correspondingly tiny distances. This is also why we cannot currently test Planck scale physics experimentally. The energy required to probe 10 to the power of minus 35 meters is on the order of the Planck energy, about 10 to the power of 19 giga-electron volts. The Large Hadron Collider operates at around 10 to the power of 4 giga-electron volts. That is 15 orders of magnitude lower. Building an accelerator capable of reaching Planck energy using conventional technology would require a machine larger than the observable universe. The gap is not incremental, it is astronomical. So the Planck length remains a theoretical boundary, rather than an experimentally measured one. Its extreme smallness is not arbitrary. It arises because gravity is extraordinarily weak compared to quantum forces. It arises because the constants of nature combine in a way that isolates the scale where quantum mechanics and general relativity must both apply. And this tiny number has enormous implications. It suggests that below 10 to the power of minus 35 meters, the smooth picture of spacetime inherited from relativity cannot be maintained. It suggests that geometry itself may fluctuate. It suggests that distance, as we understand it, may cease to have operational meaning. Understanding exactly how the mathematics produces this scale, and why combining h-bar, g and c yields a length rather than some other quantity, requires looking more closely at the dimensional structure behind the Planck length, and how these constants mathematically define a natural boundary in physical law. To understand why the Planck length takes the exact form that it does, and why it represents a fundamental boundary rather than just another small number, we need to step carefully through the mathematics that produces it, not in a complicated way, but in a disciplined one. The Planck length is not guessed, it is constructed, and it emerges from a simple but powerful idea. When you combine the fundamental constants of nature in the only way that produces a quantity with dimensions of length, you uncover a scale where quantum mechanics, gravity, and relativity converge. The starting point is dimensional analysis. Dimensional analysis is not advanced mathematics. It is a method that examines the units of physical quantities. Every measurable quantity has dimensions. Length is measured in meters, time is measured in seconds, mass is measured in kilograms. Energy has dimensions of mass times length, squared divided by time squared. When physicists construct natural units, they look for combinations of constants that eliminate arbitrary human definitions and depend only on universal parameters. The Planck length comes from combining three constants. The reduced Planck constant h-bar, which has units of joule-seconds. The gravitational constant g, which has units of meters cubed per kilogram per second squared. The speed of light c, which has units of meters per second. The question is simple: how can we combine h-bar, g and c to produce something with units of length? Write down their dimensions explicitly. The dimension of h-bar is h-bar equals energy times. Time energy itself is mass times length squared over time squared. So, h-bar equals mass times length squared over time. The dimension of g is g equals length cubed over mass times time squared. The dimension of c is c equals length over time. Now we want to combine these three quantities in some arrangement such that the final dimensions reduce to length alone. Suppose we construct a quantity, L equals h bar a GBC1 thus, we need to determine the exponents a, b and c, such that the resulting dimensions equal length 1. Substitute the dimensional forms L equals mass times length squared over time to the power a times length cubed over mass times time squared to the power b times length over time to the power c. Now collect powers of mass, length and time separately. Mass contributes mass to the power of a times mass to the power of minus b equals mass to the power of a minus b. Length contributes length to the power of 2 a times length to the power of 3, b times length to the power of c equals length to the power of 2, a plus 3b plus c. Time contributes time to the power of minus a times time to the power of minus 2, b times time to the power of minus c equals time to the power of minus a minus 2, b minus c. We want the overall dimensions to be mass to the power of 0 times length to the power of 1 times time to the power of 0. So we set up 3 equations. A minus b equals 0, 2, a plus 3b plus c equals 1 minus a minus 2, b minus c equals 0. Solve the first equation, a minus b equals 0, so a equals b, substitute, e equals b into the third equation, minus a minus 2, a minus c equals 0, minus 3, a minus c equals 0, so c equals minus 3. I can now substitute a equals b and c equals minus 3a into the second equation. 2, a plus 3 a minus 3a equals 1, 2. A plus 3 a minus 3a simplifies to 2a, so 2, a equals 1 a equals 1 half. Therefore, b equals 1 half, c equals minus 3 halves. So the combination becomes L equals h bar to the 1 half power, g to the 1 half power, c to the minus 3 halves power. This can be written as L equals the square root of h bar g over c cubed, and that is the Planck length. This derivation shows something important. There is only one way to combine h bar, g and c to produce a quantity with dimensions of length. The Planck length is not one possibility among many. It is the unique natural length scale formed from those 3 constants. The same method produces the Planck time, Planck mass, and Planck energy. The Planck time is Tp equals the square root of hg over c to the 5th power. The Planck mass is Mp equals the square root of hc over g. The Planck energy is Ep equals mpc squared equals the square root of hc to the 5th power over g. Each of these scales marks a boundary where quantum mechanics and gravity become equally important. But dimensional analysis alone does not explain why this length has physical meaning. It only shows that such a length exists mathematically. To understand why it matters physically, we need to connect it to measurable quantities. Consider 2 characteristic lengths that arise independently in physics. First, the Compton wavelength of a particle with mass m. Lambda c equals h bar over mc. This length measures the quantum uncertainty associated with a particle's position. It sets the scale below which the concept of a localized particle becomes fuzzy due to quantum effects. Second, the Schwarzschild radius of a mass mia por s equals 2gm over c squared. This length measures the gravitational radius associated with a mass. If an object is compressed within this radius, it forms a black hole. Now compare these 2 lengths. The Compton wavelength decreases as mass increases. The Schwarzschild radius increases as mass increases. There must be a mass for which these 2 lengths are equal. Set h bar over mc equals 2 gm over c squared. Multiply both sides by m, h bar over c equals 2 gm squared over c squared. Multiply both sides by c squared, h bar c equals 2 gm squared. Solve for m squared equals h bar c over 2g. Ignoring the factor of 2 for order of magnitude reasoning, this gives m approximately square root of h c over g. That is the Planck mass. Now, substitute this mass back into either expression to find the corresponding length. Using the Compton wavelength, lambda approximately h over mc. Substitute m equals square root of hc over g. Lambda approximately h over c square root of hc over g. Simplify. Lambda approximately square root of hg over c cubed, which is the Planck length. This shows that the Planck length is the scale at which quantum uncertainty and gravitational collapse coincide. Below this scale, trying to localize a particle more precisely would require energy sufficient to create a black hole. The region would no longer be accessible to measurement. This is not just dimensional coincidence. It reflects a fundamental conflict between quantum mechanics and general relativity. Quantum mechanics says that reducing position uncertainty increases momentum uncertainty, and therefore energy uncertainty. General relativity says that concentrating enough energy in a small region curves space-time and can produce an event horizon. The Planck length is the point where these two statements intersect. Another way to see this is through energy density. The Planck energy density is roughly ROP approximately c to the 7th power over ag squared. This is an enormous number. It represents the energy density at which quantum gravitational effects dominate. The early universe, during the first Planck time after the Big Bang, would have approached this density. At lower densities, space-time curvature can be described classically. At Planck density, classical geometry fails. The mathematics therefore reveals something subtle but powerful. The Planck length is not small simply because we multiplied small numbers. It is small because gravity is weak and quantum uncertainty is fundamental. The scale at which these effects balance is driven to extreme values. In theoretical physics, it is often convenient to use natural units, where c equals 1 and h bar equals 1. In that system, the Planck length simplifies to Lp equals the square root of g. The smallness of Lp then directly reflects the smallness of g in those units. The gravitational coupling constant at particle energies is roughly Ge squared over hc to the 5th power. At energies accessible in accelerators, this number is minuscule. Only when E approaches the Planck energy does this coupling become of order 1. So mathematically, the Planck length is the scale at which dimensionless gravitational coupling becomes strong. This is similar to how the Bohr radius defines the characteristic scale of hydrogen atoms, or how the classical electron radius defines a scale associated with the electromagnetic self-energy. The Planck length defines the scale of quantum gravitational interaction. The difference is that the Planck scale lies far beyond direct experimental reach. Dimensional analysis alone cannot prove that space is discrete at this scale. It cannot prove that there is a smallest possible distance in an absolute sense. What it shows is that below LP our existing frameworks cannot remain independent. Quantum mechanics and gravity must be unified, and since we do not yet possess a complete theory of quantum gravity, the mathematics signals a boundary rather than a final answer. Still, the derivation is striking in its simplicity. By combining three constants, we obtain a unique length scale that appears repeatedly in discussions of black holes, early cosmology, and high-energy physics. The Planck length is not arbitrary. It is mathematically inevitable once you accept that h bar, g, and c are fundamental. What remains to explore is what happens to spacetime itself as we approach this scale, and how the smooth geometry described by general relativity begins to break down when quantum fluctuations of gravity can no longer be ignored. For most of the 20th century, physics advanced along two remarkably successful but largely separate tracks. On one side stood quantum mechanics, describing atoms, particles, and microscopic interactions with extraordinary precision. On the other side stood general relativity, describing gravity, black holes, and the large-scale structure of the universe. Each theory has been tested extensively within its domain. Each has passed every experimental challenge so far, Yet they are built on fundamentally different assumptions about reality. Quantum mechanics assumes a fixed background of space and time. Events occur at coordinates defined within a stable geometric arena. Fields fluctuate, particles interact, probabilities evolve, but the stage itself remains intact. General relativity does not treat space and time as a fixed stage. It treats them as dynamic. Mass and energy curve space-time. Geometry itself responds to matter. There is no rigid background independent of physical content. For everyday scales, this difference does not cause conflict. At atomic scales, gravitational curvature is negligible. At planetary and galactic scales, quantum uncertainty is negligible. The theories can be applied independently with no noticeable inconsistency. The problem emerges only under extreme conditions. Imagine compressing matter to extremely high densities. Imagine energy so large that quantum fluctuations are no longer small corrections but dominant effects. At those scales, you cannot ignore gravity, but you also cannot ignore quantum mechanics. That intersection occurs near the Planck length. To see why, consider what each theory says about measurement. Quantum mechanics imposes the uncertainty principle. Delta x times delta p greater than or equal to h bar over 2. If you attempt to localize a particle within a region delta x, the uncertainty in its momentum delta p increases. Because momentum relates to energy, confining a particle tightly implies high energy fluctuations. Now consider what general relativity says about energy. Energy and mass curve space-time. According to Einstein's field equations, the curvature of space-time is proportional to the energy-momentum content present. So increasing energy concentration in a small region increases curvature. As you attempt to measure positions with ever greater precision, quantum mechanics forces you to use higher energies. But higher energies increase gravitational curvature. Eventually, these two effects collide. Suppose you try to localize an event within a region smaller than the Planck length. The required energy uncertainty becomes so large that the associated Schwarzschild radius exceeds the size of the region. Instead of resolving a smaller structure, you create a microscopic black hole. The region becomes hidden behind an event horizon. Information about smaller distances becomes inaccessible. This is where relativity meets quantum mechanics in a literal operational sense. It is not simply a matter of equations failing to agree, it is a physical limitation. The very act of probing smaller scales changes the geometry of space-time itself. To appreciate how different these frameworks are, consider how each treats time. In quantum mechanics, time is an external parameter. The Schrödinger equation describes how a wave function evolves with respect to time. Time is not quantized. It flows independently of the system. In general relativity, time is part of space-time geometry. It can slow down near massive objects. It can dilate due to velocity. It can curve along with spatial dimensions. Trying to merge these views leads to conceptual tension. If space-time itself fluctuates quantum mechanically, what does it mean to have a well-defined time parameter? If geometry is uncertain, how do you define evolution with respect to it? These questions become unavoidable at the Planck scale. One way to see the conflict mathematically is through attempts to quantize gravity in the same way as other forces. Quantum field theory works well for electromagnetism, the weak force, and the strong force. In each case, you treat the force as mediated by a quantum field defined on a background space-time. When physicists attempt to apply the same procedure to gravity, treating the gravitational field as a quantum field, they encounter divergences that cannot be removed using standard renormalization techniques. The gravitational coupling constant has negative mass dimension. This technical statement has important consequences. It means that quantum corrections to gravity grow stronger at higher energies. The theory becomes non-renormalizable in the traditional sense. At low energies, quantum gravitational effects are negligible, but as energy approaches the Planck scale, these corrections become uncontrollable within the framework of conventional quantum field theory. This signals that a new approach is required. The Planck length therefore marks not just a numerical boundary, but a conceptual one. It is the scale at which our two most successful theories cannot be kept separate. Consider black holes. Black holes are predicted by general relativity. They are regions where gravity is so strong that nothing, not even light, can escape. Classical general relativity predicts that black holes contain singularities, points of infinite density where curvature becomes infinite. Singularities are a sign that a theory is incomplete. Infinite curvature suggests that classical geometry has broken down. Now add quantum mechanics. In the 1970s, Stephen Hawking showed that black holes are not entirely black. Quantum effects near the event horizon cause them to emit radiation, now called Hawking radiation. This process involves quantum fluctuations in curved space-time. The temperature of a black hole is inversely proportional to its mass. As a black hole radiates, it loses mass. If it continues shrinking, it eventually approaches the Planck mass. At that point, its radius approaches the Planck length. The final stages of black hole evaporation require a full theory of quantum gravity. Neither general relativity nor quantum field theory alone can describe what happens at that scale. Another example comes from cosmology. If you trace the expansion of the universe backward in time, density and temperature increase. According to classical general relativity, the universe began at a singularity, a point of infinite density and zero volume. But near 10 to the power of minus 43 seconds after the Big Bang, roughly 1 Planck time, the energy density would have reached the Planck scale. Quantum gravitational effects would dominate. Without a theory that unifies relativity and quantum mechanics, we cannot describe what happened before that epoch. So the Planck scale is not a minor detail in theoretical physics. It defines the earliest moments of the universe and the deepest interiors of black holes. In practical terms, the conflict between relativity and quantum mechanics does not affect daily life. GPS satellites require corrections from relativity. Semiconductors rely on quantum mechanics, but neither requires quantum gravity. The gap between accessible energies and the Planck scale isolates the problem from experimental testing. Still, the logical necessity of unification remains. Several candidate theories attempt to bridge the gap. String theory replaces point particles with one-dimensional strings, whose characteristic length is near the Planck scale. In this framework, gravity emerges naturally from certain vibrational modes. The finite size of strings softens ultraviolet divergences that plague point particle gravity. Loop quantum gravity takes a different approach. It attempts to quantize spacetime itself. In this theory, geometry becomes discrete at the Planck scale. Areas and volumes have quantized spectra. Space is composed of networks of finite loops. Both approaches predict that classical smooth spacetime is an approximation valid only at scales much larger than LP. Despite decades of work, no experimental evidence has yet confirmed either framework. The reason is clear. The Planck scale is remote. Even the highest energy cosmic rays detected fall far below Planck energy. Yet the theoretical argument remains strong. If quantum mechanics is correct, and if general relativity is correct, and if both apply universally, then they must intersect at some scale. That scale is determined by combining h bar, g, and c. The result is LP. This convergence is not optional. It follows directly from the structure of the theories. Where relativity meets quantum mechanics, geometry can no longer be treated as smooth and fixed. It becomes subject to uncertainty. Distance, time, curvature, all may fluctuate. The Planck length therefore marks the boundary where spacetime itself must be described quantum mechanically. Understanding what that description looks like requires examining how classical spacetime breaks down under quantum fluctuations, and what it means for geometry to lose its smooth character at extremely small scales. Up to this point, spacetime has been treated as a geometric framework that becomes problematic only at extremely small scales. Now we need to examine what it actually means for space-time to break down. That phrase does not imply that space suddenly disappears, or that distances stop existing in some dramatic sense. It means that the classical description of geometry, smooth, continuous, differentiable, can no longer be assumed to hold when quantum effects of gravity become significant. General relativity describes space-time as a four-dimensional manifold equipped with a metric. The metric tells you how to measure distances and times between nearby points. It allows you to calculate curvature. It defines geodesics, which determine how particles move when acted upon only by gravity. The mathematics of general relativity assumes that this manifold is smooth. At every point you can define derivatives. You can talk about infinitesimally small intervals. Curvature can be calculated precisely at arbitrarily small scales. This smoothness assumption works remarkably well across all experimentally accessible regimes. Planetary orbits, gravitational lensing, time dilation near massive objects, all follow predictions based on a continuous geometry. Quantum mechanics introduces a different kind of structure. In quantum field theory, fields are defined over space-time. Particles arise as excitations of these fields. But even here, the underlying space-time is treated as continuous. The quantum uncertainty applies to fields and particles, not to the geometry itself. The breakdown occurs when we try to treat the gravitational field, the metric itself, as a quantum object. If geometry is subject to quantum uncertainty, then at sufficiently small scales the metric cannot be sharply defined. Just as the position of a particle has intrinsic uncertainty, the curvature of space-time may fluctuate. Consider the role of energy in quantum mechanics. Due to the uncertainty principle, energy can fluctuate for short times. Virtual particles appear and disappear in the vacuum. These fluctuations are normally small corrections in flat or weakly curved space-time. But when gravity is included, energy fluctuations imply curvature fluctuations. At ordinary scales, the gravitational effect of vacuum fluctuations is negligible. But as we examine smaller and smaller regions, the energy density associated with fluctuations increases. If you confine a fluctuation to a region of size L, the characteristic energy uncertainty scales roughly as h bar c over L. As L decreases, the energy uncertainty increases. Gravity responds to energy density. If enough energy is concentrated within a small region, the curvature becomes strong. Near the Planck length, the estimated energy fluctuations within a region of that size are sufficient to curve space-time significantly. This suggests that at distances comparable to ELLP, geometry cannot remain smooth. It becomes dominated by quantum fluctuations. John Wheeler described this regime as quantum foam. The term is not precise mathematics, but a conceptual guide. It suggests that at extremely small scales, space-time resembles a turbulent structure rather than a smooth surface. Instead of a stable metric defined at every point, the geometry may fluctuate violently. Tiny regions could briefly form microscopic black holes or wormhole-like structures before evaporating. Distances may not have definite values. The topology of space-time itself may fluctuate. This is what is meant by the breakdown of classical space-time. It is important to understand that this breakdown does not occur gradually at everyday scales. It is confined to distances near LP. At scales even slightly larger than the Planck length, fluctuations average out and smooth geometry re-emerges. This is similar to how a fluid appears continuous at macroscopic scales even though it is composed of molecules. If you zoom in far enough, the assumption of continuity fails. But at scales much larger than molecular spacing, continuum mechanics works perfectly. The analogy is imperfect, because in the case of spacetime we do not yet know whether there are discrete atoms of geometry. But the principle is similar. Smoothness may be an approximation valid only above a certain scale. The breakdown also affects the concept of locality. In classical physics, you can define arbitrarily small neighborhoods around points. You can specify the value of a field at an exact coordinate. But if spacetime geometry fluctuates at the Planck scale, the notion of an exact point may lose meaning. Without a well-defined metric at arbitrarily small scales, distances between nearby events cannot be specified precisely. The classical idea of a point as a location with zero extent becomes problematic. This has implications for quantum field theory. Standard quantum field theory assumes that fields are defined at each point in space-time. Interactions occur locally at precise coordinates. If the background geometry is uncertain, this framework must be modified. Another aspect of breakdown appears in the presence of singularities. In general relativity, singularities arise when curvature becomes infinite. The center of a classical black hole and the initial state of the Big Bang are examples. Infinite curvature signals that the theory has reached its limit of applicability. Quantum gravity is expected to resolve singularities by replacing them with finite structures. But without a complete theory, we cannot yet describe how this resolution occurs. What we can say is that the Planck scale sets the boundary beyond which classical curvature calculations are no longer reliable. It is useful to quantify this boundary. The Riemann curvature tensor measures how spacetime bends. In regions where curvature components become comparable to 1 over LP squared, quantum corrections cannot be neglected. At such curvatures, fluctuations in geometry become as large as the background curvature itself. In other words, the geometry is no longer a small perturbation around a smooth structure. It is inherently uncertain. This breakdown also challenges the concept of causality at extremely small scales. In classical space-time, light cones define causal structure. Events inside the light cone can influence one another. Events outside cannot. But if geometry fluctuates, light cones may fluctuate as well. The distinction between time-like and space-like separation could become ambiguous over Planck scale intervals. However, these fluctuations are expected to be suppressed at larger scales. Causality remains intact at macroscopic distances. Another consequence concerns the renormalization of gravity. In quantum field theory, divergences arise when interactions are calculated at arbitrarily small distances. For most forces, these divergences can be absorbed into redefined parameters. Gravity behaves differently. Its coupling grows stronger at higher energies. This growth reflects the fact that probing shorter distances increases gravitational effects. The non-renormalizability of gravity in conventional quantum field theory is a mathematical signal of breakdown. Several approaches attempt to address this. String theory introduces a fundamental length scale associated with the size of strings. Because strings are not point-like, interactions are smeared over finite distances. This softens ultraviolet divergences and avoids some of the infinities encountered in point-particle gravity. Loop quantum gravity takes a different approach. It suggests that space-time itself is composed of discrete elements. Areas and volumes are quantized in units related to LP squared and LP cubed. In this framework, there are no infinitely small distances. The discrete structure prevents singularities. In both cases, the smooth manifold of general relativity emerges only as an approximation valid at scales much larger than the Planck length. The breakdown of space-time does not mean that reality dissolves into chaos. It means that the mathematical description of geometry must change. The variables used in classical relativity, metric components defined at each point, may not be the correct degrees of freedom at the smallest scales. Instead, geometry may be described by algebraic structures, networks, or extended objects. One reason this breakdown is difficult to explore experimentally is that Planck scale fluctuations are incredibly small and short-lived. The Planck time is about 10 to the power of minus 43 seconds. Any fluctuation occurring on that timescale is far beyond direct measurement. Nevertheless, some researchers have speculated about indirect signatures. Tiny deviations in the propagation of high-energy photons over cosmological distances might reveal Planck scale effects. So far, no confirmed evidence has been found. The The breakdown of space-time is therefore primarily a theoretical conclusion derived from consistency requirements. If both quantum mechanics and general relativity are correct, and if both apply universally, then there must be a scale where their assumptions conflict. That scale is LP. At distances much larger than LP, classical geometry is accurate. At distances near LP, geometry fluctuates. Below LP, classical notions of distance and duration may not be meaningful. This leads directly to the next fundamental question. If smooth spacetime breaks down at the Planck scale, does that mean space itself is made of discrete elements? Or is it still continuous but governed by new rules? If classical spacetime breaks down near the Planck scale, the next natural question is whether space itself has an underlying discrete structure. When we say discrete, we mean composed of indivisible units, rather than being infinitely divisible. This is not a trivial shift in language. It challenges one of the oldest assumptions in mathematics and physics, that space is continuous. In classical geometry, space is modelled as a continuum. Between any 2 points, there are infinitely many other points. You can divide a line segment in half, then in half again, indefinitely, without ever reaching a smallest piece. This assumption is deeply embedded in calculus and differential geometry, which form the mathematical backbone of modern physics. General relativity relies on this continuity. The curvature of space-time is defined through derivatives, which require smoothness at arbitrarily small scales. Without continuity, the standard formulation of Einstein's equations would not make sense. Yet quantum mechanics has already forced physics to abandon continuity in other contexts. Energy levels in atoms are discrete. Angular momentum is quantized. Electromagnetic radiation is exchanged in quanta. The transition from classical to quantum descriptions repeatedly replaces smooth variation with stepwise structure. It is reasonable, then, to ask whether space itself might also be quantized. One of the main theoretical frameworks that proposes a discrete structure for space is loop quantum gravity. This approach begins by attempting to quantize general relativity directly, without introducing new fundamental objects like strings. Instead of treating spacetime as a smooth manifold with a metric field, loop quantum gravity reformulates general relativity in terms of variables better suited for quantization. In this framework, the geometry of space is described by spin networks. A spin network is a graph-like structure consisting of nodes connected by edges. Each edge carries quantum numbers that determine discrete amounts of area, and each node corresponds to discrete units of volume. The key result is that area and volume operators have discrete spectra. That means that surfaces and regions of space cannot have arbitrarily small areas or volumes. They come in quantized units, with minimum values on the order of the Planck length squared for area and the Planck length cubed for volume. In such a picture, space is not continuous at the smallest scales. It is composed of finite elements, though not arranged in a regular grid. The structure is combinatorial rather than geometric in the classical sense. However, this does not mean space is made of tiny cubes. The discrete elements in loop quantum gravity are more abstract. They represent quanta of geometry rather than solid building blocks. At scales much larger than the Planck length, these discrete units collectively approximate smooth space, just as atoms collectively approximate a continuous fluid. Another approach, string theory, offers a different perspective. In string theory, the fundamental entities are not point particles but one-dimensional strings. These strings have a characteristic length scale close to the Planck length. Because strings have finite extent, interactions are spread out over small regions rather than occurring at exact points. This finite size helps avoid certain divergences that plague point-particle theories of quantum gravity. However, string theory does not necessarily imply that space itself is discrete. The background space-time in many formulations of string theory remains continuous, though modified by additional dimensions and extended objects. There are also more radical proposals suggesting that spacetime is emergent rather than fundamental. In some interpretations of quantum gravity and holography, space may arise from patterns of entanglement in a deeper quantum system. In these models, geometry is not the starting point but a derived concept. The holographic principle, inspired by black hole thermodynamics, suggests that the information content of a region of space is proportional not to its volume, but to its surface area measured in Planck units. This implies that the number of fundamental degrees of freedom inside a region is finite, and scales with area rather than volume. Such arguments hint at an underlying discreteness in the informational structure of space, even if the geometry appears smooth at larger scales. To understand why discreteness might be necessary, return to the problem of measurement. If space were infinitely divisible, one could in principle localize events to arbitrarily small regions. But as discussed earlier, quantum mechanics and gravity together prevent localization below the Planck length. Attempting to probe smaller distances requires energy densities that create black holes. This operational limitation suggests that distances smaller than LP cannot be meaningfully distinguished. Even if space were mathematically continuous, physically measurable distances might have a lower bound. The distinction between mathematical continuity and physical discreteness is important. A theory may use continuous mathematics while still predicting minimal measurable quantities. For example, classical electromagnetism uses continuous fields, yet electric charge is quantized. Similarly, spacetime might be described by continuous variables at the fundamental level, while observable geometric quantities come in discrete units. There is also a conceptual question about what discreteness means for symmetry. Continuous space supports continuous symmetries such as rotational invariance. A simple lattice of points would break such symmetries unless the spacing were extremely fine and isotropic. Any discrete theory of space must preserve Lorentz invariance, the symmetry underlying special relativity, at observable scales. Achieving this while introducing fundamental discreteness is non-trivial. Loop quantum gravity claims to preserve local Lorentz invariance in its formulation. The discrete structure does not correspond to a fixed background grid, but to quantum states of geometry that respect symmetry statistically at large scales. Still, these ideas remain theoretical. No direct experimental evidence currently confirms that space is discrete. Some researchers have proposed that Planck-scale discreteness might lead to tiny violations of Lorentz invariance at extremely high energies. Observations of gamma-ray bursts and other astrophysical phenomena have placed stringent constraints on such deviations, but so far no confirmed signal has been detected. Another way to approach the question is to consider entropy in information. Black hole entropy is proportional to the area of the event horizon divided by the Planck length squared. This suggests that the fundamental units of information in a region are counted in Planck area patches. If space were infinitely divisible, one might expect infinite information density. But black hole thermodynamics indicates a finite information capacity per unit area. This supports the idea that space may have a finite number of degrees of freedom per region, consistent with some form of discreteness. However, discreteness at the Planck scale does not imply that space is granular in a way that would be visible even under powerful microscopes. The scale is so small that any discrete structure would be undetectable with current technology. Even if space consists of Planck-scale quanta, the spacing between them is 10 to the power of minus 35 meters. Atomic scales are 10 to the power of minus 10 meters. The ratio is 10 to the power of 25. That gap ensures that classical smoothness remains an excellent approximation for all practical purposes. So is space made of something discrete? At present, we do not know definitively. Some theories predict it, others do not require it. What we can say is that classical continuity cannot be assumed without modification at the Planck scale. The possibility of discreteness arises because the Planck length sets a limit below which localization loses operational meaning. If there is a smallest measurable length, it is natural to consider that space itself may have a smallest structural unit. Whether this unit is a literal pixel of geometry, a node in a spin network, a fundamental string scale, or an emergent property of quantum entanglement remains an open question. What is clear is that at distances near LP the smooth manifold of classical relativity is no longer sufficient. Something new must replace it. Understanding what that something looks like in more detail requires examining how quantum fluctuations of geometry behave at the Planck scale, and how concepts like quantum foam attempt to describe the texture of reality at its smallest possible scale. When we describe space at everyday scales, we treat it as smooth and stable. Distances remain fixed unless influenced by gravity. Objects move through space, but space itself does not flicker or fluctuate in any noticeable way. Even in general relativity, where space-time curves in response to mass and energy, the curvature changes continuously and predictably. However, once quantum mechanics is applied to gravity, this calm picture begins to shift. If all physical fields are subject to quantum fluctuations, and if gravity is mediated by a field associated with spacetime geometry itself, then geometry should also fluctuate. At sufficiently small scales, these fluctuations may become dominant rather than negligible. This is the context in which the idea of quantum foam arises. The term was introduced by John Wheeler in the 1950s. Wheeler proposed that at distances on the order of the Planck length, space-time would not resemble a smooth manifold. Instead, it would appear highly irregular and dynamic, with violent fluctuations in curvature occurring over extremely short intervals. To understand why such fluctuations are expected, consider how quantum field theory treats the vacuum. In classical physics, a vacuum is empty space. In quantum field theory, the vacuum is the lowest energy state of all fields. It is not empty in the classical sense. Due to the uncertainty principle, fields cannot remain exactly zero everywhere. They fluctuate around their minimum energy configuration. These fluctuations give rise to virtual particles. Particle-antiparticle pairs appear and annihilate within time intervals, allowed by the uncertainty principle. Though virtual particles cannot be observed directly, their effects are measurable in phenomena such as the Casimir effect and corrections to atomic energy levels. If electromagnetic fields fluctuate in vacuum, and if gravitational fields are also subject to quantum principles, then space-time curvature itself should fluctuate. At large scales, these fluctuations average out. Their effects are too small to notice. But as the scale shrinks toward the Planck length, the amplitude of fluctuations becomes comparable to the scale itself. To estimate this, consider again the energy uncertainty in a region of size L. Quantum mechanics suggests that energy fluctuations on the order of h bar c over L may occur within a time interval of order L over c. As L decreases, the associated energy uncertainty increases. Because gravity couples to energy, these fluctuations imply curvature fluctuations. The smaller the region, the stronger the relative curvature effects. At L, approximately LP, the estimated curvature fluctuations become so large that they are comparable to 1 over LP squared, the scale of Planck curvature. This means that spacetime cannot remain smooth at that scale. The geometry itself becomes uncertain. Wheeler described this regime metaphorically as a foam of transient structures. Tiny black holes could form and evaporate within Planck times. Wormhole-like connections between different regions might appear and disappear. The topology of spacetime might not be fixed but fluctuating. It is important to emphasize that quantum foam is not a fully developed theory. It is a heuristic picture that captures the expectation of strong fluctuations at the Planck scale. The mathematics required to describe these fluctuations precisely depends on a complete theory of quantum gravity, which we do not yet possess. Nevertheless, the concept highlights a fundamental change in perspective. Classical geometry assumes that at every point in spacetime, curvature can be defined precisely. Quantum foam suggests that at sufficiently small scales, such precision is impossible. Instead of a smooth metric, there may be a superposition of possible geometries. In standard quantum mechanics, a particle can exist in a superposition of positions. In quantum gravity, spacetime itself may exist in a superposition of geometries. This idea challenges our intuition. We are accustomed to thinking of geometry as the framework within which quantum states exist. But near the Planck scale, geometry becomes part of the quantum system. One way to formalize this is to consider a quantum state of the gravitational field. Instead of a single classical metric, there may be a wave functional that assigns amplitudes to different possible geometries. In such a description, spacetime does not have a definite shape at the smaller scales. Only at larger scales does a classical geometry emerge as an effective description. The emergence of smooth geometry from underlying fluctuations may be similar to how macroscopic properties emerge from microscopic randomness. For example, temperature emerges from the collective motion of molecules. No single molecule possesses temperature. It is a statistical property of many particles. Similarly, smooth spacetime may emerge from averaging over Planck scale fluctuations. There is also a connection between quantum foam and black hole physics. The entropy of a black hole is proportional to the area of its event horizon divided by LP squared. This suggests that Planck scale units of area are fundamental in counting microscopic degrees of freedom. If the horizon area is built from Planck area elements, then geometry at the smallest scales may have a discrete informational structure. The holographic principle extends this idea further. It proposes that the maximum information contained in a region scales with its surface area rather than its volume. This principle is consistent with black hole thermodynamics and implies that spacetime may have a finite number of degrees of freedom per Planck area. In some approaches to quantum gravity, quantum foam is not merely random noise but has structure determined by deeper principles. For example, in loop quantum gravity, the spin network states that describe geometry can be interpreted as providing a discrete texture to space. In string theory, extended objects and dualities suggest that distances below a certain scale may not be physically distinguishable from larger distances under certain transformations. Regardless of the specific framework, most theoretical approaches agree that classical spacetime is an approximation valid at scales much larger than ELP. It is also important to consider experimental prospects. If quantum foam exists, could it leave observable traces? Some proposals suggest that Planck scale fluctuations might affect the propagation of high-energy photons over cosmological distances. Tiny variations in arrival times or polarization patterns could reveal underlying granularity. So far, observations of distant gamma-ray bursts and other astrophysical sources have not confirmed such effects. The constraints are increasingly tight, suggesting that any Planck scale structure must preserve Lorentz invariance to extremely high precision. This reinforces the idea that even if space has a discrete or fluctuating texture at LP, it must average out in a way that maintains the symmetries observed at larger scales. The phrase texture of reality is sometimes used to describe this Planck scale regime. It implies that spacetime has an internal structure, not visible at everyday scales but fundamental at the smallest distances. However, this texture is not made of matter. It is not a medium in the classical sense. It is a property of geometry itself. Understanding this texture requires unifying quantum mechanics and general relativity in a consistent framework. Until that is achieved, quantum foam remains a conceptual guide rather than a complete description. What is clear is that the Planck length marks the threshold where geometry becomes uncertain, curvature fluctuates strongly, and the smooth manifold of classical relativity dissolves into a regime governed by quantum principles. The implications of this breakdown extend beyond abstract mathematics. They influence how we think about black holes, the earliest moments of the universe, and the ultimate limits of measurement. Black holes are often introduced as extreme astrophysical objects formed from collapsing stars, but in the context of the Planck length they serve a different purpose. They reveal something fundamental about the limits of measurement itself. When gravity and quantum mechanics are combined, black holes emerge not only as cosmic phenomena, but as boundaries that prevent us from probing arbitrarily small distances. To understand why, begin with the classical picture. According to general relativity, if a sufficient amount of mass or energy is compressed into a region smaller than its Schwarzschild radius, a black hole forms. The Schwarzschild radius is given by Graph equals 2 gm over c squared. If an object is confined within that radius, the escape velocity exceeds the speed of light. An event horizon forms, separating the interior from the outside universe. Now consider measurement at very small scales. In quantum mechanics, resolving smaller distances requires shorter wavelengths. Shorter wavelengths correspond to higher momentum. Higher momentum implies higher energy. If you want to probe a distance L, the typical energy required is on the order of h bar c over L. As L decreases, the required energy increases. Suppose you attempt to measure a position with uncertainty delta x. To achieve delta x approximately equals L, you need energy on the order of E approximately equals h bar c over L, but energy contributes to gravitational curvature. If that energy is localized within a region of size L, it has an associated Schwarzschild radius. Rs, approximately 2ge over c, to the fourth substitute E approximately hc over L. Rs, approximately 2g hc over c to the fourth Rs, approximately 2gh over c cubed L. Now ask what happens when the Schwarzschild radius becomes comparable to L itself. Set Rs approximately equals L. L approximately equals 2gh over c cubed L. Multiply both sides by L. L squared approximately equals 2gh over c cubed. Ignoring the factor of 2 for order of magnitude reasoning, L approximately equals the square root of hg over c cubed. That is the Planck length. This calculation shows something important. When you attempt to localize energy within a region smaller than Lp, the Schwarzschild radius associated with that energy exceeds the size of the region. In other words, you create a black hole larger than the region you're trying to probe. The act of measurement defeats itself. The event horizon prevents information from escaping. The region becomes inaccessible. This is not a technological limitation. It is a fundamental one, derived from the laws of quantum mechanics and general relativity. Black holes therefore define an operational boundary. In classical physics, you could imagine zooming in on smaller and smaller scales without limit. In quantum field theory without gravity, the same assumption holds mathematically. But once gravity is included, arbitrarily small localization is impossible. This is why black holes are central to discussions of the Planck length. They enforce a minimum measurable length scale. The story becomes even more interesting when quantum effects are included in black hole physics. Stephen Hawking showed in 1974 that black holes emit radiation due to quantum effects near the event horizon. This radiation has a temperature given by T approximately hc cubed over 8 pig mk sub b, where k sub b is Boltzmann's constant. As a black hole loses mass through radiation, its temperature increases. Smaller black holes are hotter. If a black hole were reduced to Planck mass, its radius would be on the order of the Planck length, and its temperature would approach the Planck temperature. At that point, classical general relativity can no longer describe the system reliably. Quantum gravitational effects dominate. This suggests that the Planck scale defines the smallest meaningful black hole. If you attempt to create a black hole with mass smaller than the Planck mass, quantum uncertainty in its energy becomes comparable to its total mass. The concept of a well-defined event horizon breaks down, so the Planck mass and Planck length define a boundary not only for measurement, but also for the very concept of a black hole. Black hole entropy further strengthens this connection. The entropy of a black hole is proportional to the area of its event horizon, divided by 4 times Lp squared, S equals area, divided by 4lp². This formula implies that the fundamental units of information associated with a black hole are counted in Planck area patches. The appearance of lp² in the entropy formula suggests that Planck-scale geometry plays a direct role in the microscopic structure of space-time. If each Planck area unit corresponds to a fundamental degree of freedom, then the Planck length sets the scale of information storage in the universe. The holographic principle builds on this insight. It proposes that the maximum amount of information contained within a region of space is proportional to its surface area measured in Planck units, not its volume. This idea challenges classical intuition. In ordinary systems, entropy scales with volume. In gravitational systems near black holes, it scales with area. That shift suggests that at fundamental levels, space may have a finite number of degrees of freedom per Planck area. Black holes also reveal tensions between quantum mechanics and general relativity in the form of the information paradox. If a black hole forms from matter in a pure quantum state and then evaporates completely through Hawking radiation, what happens to the information about the initial state? Classical Hawking radiation appears thermal, carrying no detailed information. If the black hole disappears entirely, information would be lost, but quantum mechanics forbids information loss in isolated systems. Resolving this paradox requires a full theory of quantum gravity. Many proposals involve Planck-scale physics near the event horizon or in the black hole interior. Again, the Planck length appears as the boundary where new physics must intervene. Beyond astrophysical black holes, one can consider hypothetical microscopic black holes formed in high-energy collisions. If particle accelerators could reach Planck energies, they might produce tiny black holes with radii on the order of LP. Such objects would evaporate almost instantly. Their behavior would provide direct insight into quantum gravity. However, current accelerators operate far below the required energy scale. The Planck energy is about 10 to the power of 19 giga-electron-volts, while the Large Hadron Collider reaches about 10 to the power of 4 giga-electron-volts. The gap is enormous. Black holes therefore remain primarily theoretical tools for understanding Planck-scale limits rather than laboratory probes. What they demonstrate clearly is that gravity imposes a fundamental constraint on measurement. Attempting to resolve distances below LP leads to gravitational collapse. In this sense, black holes act as cosmic sensors. They prevent access to arbitrarily small scales. The breakdown of classical spacetime at singularities further reinforces this conclusion. Inside a classical black hole, curvature increases without bound as one approaches the singularity, but infinite curvature signals the breakdown of general relativity. A quantum theory of gravity is required to describe what happens when curvature approaches Planck values. Most researchers expect that singularities are replaced by finite, Planck-scale structures in a complete theory. Instead of infinite density, there may be extremely dense but finite configurations governed by quantum gravity. Similarly, the initial singularity of the Big Bang may be replaced by a Planck-scale quantum state, rather than a point of zero volume. In both cases, black holes and cosmological singularities point toward the same conclusion. Classical geometry fails at Planck scales. The limits of measurement imposed by black holes are therefore not isolated curiosities. They are consistent with the broader expectation that LP marks the smallest meaningful length scale in nature. Understanding how this limit affects the earliest moments of the universe requires turning from black holes to cosmology and examining how the Planck scale shaped the beginning of spacetime itself. When we trace the history of the universe backward in time, using the equations of general relativity, we find that density and temperature increase without bound. Galaxies move closer together, matter becomes hotter and more compressed. Eventually, classical calculations predict a singularity, a state of infinite density and zero volume at time zero. But singularities are not physical objects. They are signals that a theory has reached the edge of its applicability. Just as infinite curvature inside a black hole indicates that general relativity is incomplete there, The cosmological singularity indicates that classical gravity cannot describe the earliest moments of the universe. To understand what happened at the beginning, we must examine the Planck scale. The Planck time is approximately 5.39 times 10 to the power of minus 44 seconds. This is the time it takes a light to travel one Planck length. The Planck temperature is around 1.4 times 10 to the power of 32 Kelvin. The Planck energy density is enormous, roughly 10 to the power of 96 kilograms per cubic meter. These values define the regime where quantum gravitational effects cannot be ignored. According to classical cosmology, as we approach earlier times, the curvature of spacetime increases. When the curvature reaches values on the order of 1 over lambda p squared, quantum fluctuations in geometry become comparable to the curvature itself. At that point, the classical description fails. This boundary occurs roughly 1 Planck time after the beginning. For times later than about 10 to the power of minus 43 seconds, we can describe the universe using quantum field theory on a curved background. We can model particle interactions, symmetry breaking, inflation, and nucleosynthesis. These models are supported by observational evidence, including the cosmic microwave background and the abundance of light elements. But before the Planck time, the energy scale of the universe exceeds the Planck energy. The density exceeds the Planck density. The curvature exceeds Planck curvature. In that regime, neither classical general relativity nor ordinary quantum field theory is sufficient. The Planck scale therefore defines the earliest epoch that can be described using known physics. What happened before that remains uncertain. One possibility is that the classical singularity is replaced by a quantum gravitational state. Instead of a point of infinite density, the universe may have originated from a finite but extremely dense configuration governed by quantum geometry. In loop quantum cosmology, in application of loop quantum gravity to cosmological models, the Big Bang singularity is replaced by a bounce. The universe contracts to a minimum volume on the order of the Planck scale, then expands again. In this scenario, time extends beyond the Planck epoch into a pre-existing contracting phase. In certain versions of string cosmology, the early universe may have passed through phases described by dual geometries. Some models suggest that distances below the string scale cannot be distinguished from larger distances due to symmetry properties known as T-duality. There are also proposals involving quantum tunneling from a prior state. In some models, the universe could have emerged from a quantum fluctuation of a pre-existing vacuum, though such ideas remain speculative and mathematically challenging. What all these approaches share is the recognition that the Planck scale marks the boundary beyond which classical singularities must be replaced by quantum descriptions. The significance of the Planck scale in cosmology is not merely historical. It shapes the conditions from which all later structure emerged. For example, cosmic inflation, a period of rapid exponential expansion, proposed to explain the large-scale uniformity of the universe, likely began at energy scales somewhat below the Planck scale, but still extremely high. The fluctuations generated during inflation are believed to have seeded the formation of galaxies and cosmic structure. Those fluctuations originated as quantum fluctuations in fields present in the early universe. Their amplitude and statistical properties depend on high-energy physics, although inflationary energies may not have reached the Planck scale exactly. They were close enough that Planck-scale physics could influence initial conditions. Another connection appears in attempts to quantize cosmological spacetime directly. In classical general relativity, the Friedmann equations describe the expansion of the universe. They are derived from Einstein's field equations under the assumption of homogeneity and isotropy. But near the Planck epoch, these equations must be modified. Quantum gravitational corrections may alter the effective behavior of the scale factor, preventing it from reaching zero. In loop quantum cosmology, for instance, a repulsive quantum geometric effect appears at extremely high densities, halting collapse before a singularity forms. Such modifications remain theoretical, but they illustrate how the Planck scale governs the earliest dynamics of the universe. There is also a thermodynamic perspective. The entropy of the observable universe today is enormous but finite. Black hole entropy formulas suggest that the maximum entropy of a region scales with area measured in Planck units. If the early universe was in a state of extremely low entropy relative to its maximum possible entropy, that initial condition may be linked to Planck scale geometry. The arrow of time tied to entropy increase therefore traces back to conditions near the Planck epoch. Understanding why the universe began in a low entropy state remains one of the deepest open questions in physics. The answer may depend on Planck scale quantum gravity. It is worth emphasizing that the Planck scale does not necessarily represent a moment in the ordinary sense. It is a boundary of description. Beyond it, time itself may not have the classical meaning we assign to it. In some formulations of quantum gravity, time emerges from more fundamental relations. If spacetime geometry fluctuates at the smallest scales, the distinction between space and time may blur. The Planck time therefore marks not just the beginning of measurable cosmic history, but the threshold beyond which our familiar concepts of duration and distance may not apply. This has implications for cosmological observations. The cosmic microwave background provides a snapshot of the universe about 380,000 years after the Big Bang. We can infer conditions earlier than that through nuclear abundances and inflationary perturbations, but direct evidence of Planck-scale physics remains inaccessible. Any signals from that epoch would have been stretched and diluted by cosmic expansion. Nevertheless, theoretical consistency demands that the singularity predicted by classical relativity be resolved at the Planck scale. The breakdown of spacetime near LRP implies that the origin of the universe cannot be described as a point of zero volume and infinite density. Instead, it must be described by a quantum state of geometry. Whether that state involved a bounce, a tunneling event, a transition from another phase, or something else entirely remains unknown. What is certain is that the Planck scale defines the earliest meaningful boundary in cosmic history. It is the frontier beyond which classical physics cannot proceed without modification. Understanding whether we can ever test predictions about that epoch requires examining the limits of experimental access to Planck-scale phenomena and asking whether indirect evidence of quantum gravity might be detectable at lower energies. The Planck length is often described as the smallest meaningful distance in nature, but that statement immediately raises a practical question. If this scale is so fundamental, can it ever be measured directly? Or does it remain permanently beyond experimental reach? To approach this carefully, we need to separate two issues. First, what does it mean to measure a distance? Second, what would it take to probe distances as small as 10 to the power of minus 35 meters? In physics, measuring a distance usually involves scattering. You send a probe, light, electrons, protons, toward a target and analyze how it interacts. The resolution of the measurement depends on the wavelength of the probe. Shorter wavelengths reveal smaller structures. The de Broglie relation tells us that wavelength is inversely proportional to momentum. Lambda equals h over p. If you want to resolve structures of size L, you need wavelengths comparable to or smaller than L. That means you need momentum on the order of h over L. Momentum is related to energy. Higher resolution requires higher energy. At atomic scales, this is manageable. X-rays have wavelengths on the order of atomic spacing. Electron microscopes achieve even finer resolution. Particle accelerators push resolution down to nuclear and subnuclear scales. The Large Hadron Collider reaches energies of several tera-electron volts. This corresponds to resolving distances around 10 to the power of minus 19 meters. That is extraordinarily small, but still far above the Planck length. To probe distances on the order of LP approximately 10 to the power of minus 35 meters, the required energy would be on the order of the Planck energy. EP approximately the square root of hc to the power of 5 over g. Numerically, this is about 10 to the power of 19 gigaelectron volts. For comparison, the LHC reaches about 10 to the power of 4 gigaelectron volts. The gap between current accelerator energies and the Planck energy is about 15 orders of magnitude. Bridging that gap is not a matter of incremental improvement. It would require energies comparable to those present in the early universe during the first Planck time. There is also a more fundamental limitation. As discussed earlier, concentrating energy within a region smaller than the Planck length would create a black hole. The Schwarzschild radius associated with Planck energy is itself on the order of Lp. This means that even if we had access to Planck energy, attempting to localize it within a region of size Lp would generate an event horizon. The region we are trying to probe would be hidden. This is not a technological barrier. It is a consequence of combining quantum mechanics and general relativity. Measurement at that scale appears self-limiting. That said, direct measurement is not the only way to gain insight into fundamental scales. Physics often infers properties of inaccessible regimes through indirect evidence. For example, the structure of atoms was deduced long before they were imaged directly. Neutrinos were inferred from conservation laws before being detected. The question then becomes whether Planck-scale physics could leave observable imprints at lower energies. One possibility involves tiny deviations from Lorentz invariance. If spacetime has a discrete structure at the Planck scale, extremely high-energy particles travelling over cosmological distances might accumulate measurable effects. For instance, photons of different energies emitted simultaneously from distant gamma-ray bursts might arrive at slightly different times if spacetime dispersion occurs at Planck scales. So far, observations from space telescopes have placed very tight limits on such effects. No confirmed Planck-scale dispersion has been detected. Another possibility concerns primordial gravitational waves. If inflation occurred at energies not far below the Planck scale, quantum gravitational corrections might leave subtle signatures in the polarization of the cosmic microwave background. Detecting such signals would not measure LEP directly, but it could provide indirect evidence about Planck-scale physics. Current experiments are searching for primordial gravitational waves, but interpreting any detection would require careful theoretical modelling. Black hole evaporation is another potential window. If microscopic black holes could be produced in high-energy collisions, their evaporation spectrum might reveal information about quantum gravity. However, reaching energies required to create Planck-scale black holes is beyond current capabilities. Some speculative theories involving extra dimensions suggest that the effective Planck scale might be lower than traditionally assumed. In such scenarios, microscopic black holes could form at energies accessible to accelerators. No evidence for such phenomena has been observed. There are also proposals involving high-precision interferometry. Certain models predict that Planck-scale fluctuations in spacetime could introduce minute noise in the measurements of distance. Experiments such as the holometer have attempted to detect correlated noise that might indicate quantum geometric fluctuations. Thus far, results have not confirmed such effects. Another angle involves black hole entropy in information theory. The fact that black hole entropy scales with area in units of ELP squared suggests that Planck-scale geometry underlies thermodynamic properties of gravitational systems. While this does not constitute direct measurement, it strengthens the theoretical case that ELP has physical significance. The deeper question may not be whether we can measure the Planck length directly, but whether a complete theory of quantum gravity will render the question of direct measurement unnecessary. In many areas of physics, fundamental constants are not measured in isolation. Instead, they are inferred through the consistency of broader theories and experiments. For example, Planck's constant itself is not observed directly. Its value is extracted from phenomena such as atomic spectra, the photoelectric effect, and quantum Hall measurements. Similarly, the gravitational constant g is measured through macroscopic experiments involving masses and torsion balances. Its role in cosmology is inferred from astronomical observations. If a consistent theory of quantum gravity predicts specific low-energy phenomena that can be observed, then confirmation of those phenomena would indirectly confirm the Planck scale as the correct fundamental scale. It is also possible that our understanding of measurement itself must evolve. In classical thinking, smaller scales are accessed by increasing precision indefinitely. But if there is a smallest meaningful length, then measuring distances smaller than ELP may not be a coherent concept. In that case, the Planck length is not something to be measured directly. It is a limit on the meaning of measurement. This idea parallels the uncertainty principle. We do not measure delta x and delta p both with arbitrary precision. We accept that nature imposes a bound. If ELP represents a bound on spatial resolution, then asking to measure below it may be like asking to measure position and momentum simultaneously with infinite precision. It may not be physically meaningful. Despite these limitations, research continues. Quantum gravity remains one of the most active areas of theoretical physics. New mathematical frameworks are being developed. Observational cosmology is probing earlier and earlier epochs. High-energy astrophysics is testing the behavior of particles at extreme energies. Even if direct measurement of LP is impossible, its influence may be detectable in the structure of a deeper theory. For now, the Planck length occupies a unique position. It is theoretically unavoidable, mathematically well-defined, physically significant, and experimentally inaccessible. Whether future advances will allow us to probe closer to this scale remains uncertain. What is clear is that LP defines a boundary beyond which our current concepts of distance, curvature, and measurement require revision. Understanding how different theoretical approaches attempt to describe physics at that boundary brings us to the major competing frameworks of quantum gravity, including string theory and loop quantum gravity, which offer distinct pictures of what happens at the smallest possible scale. When physicists say that general relativity and quantum mechanics must meet at the Planck scale, that statement is not just philosophical, it is a technical demand. Both theories are extraordinarily successful within their domains, but they are mathematically incompatible when pushed into the same regime. The Planck length marks the scale where that incompatibility can no longer be ignored. Two of the most developed attempts to resolve this conflict are string theory and loop quantum gravity. They approach the problem from very different starting points, and they produce very different pictures of what reality might look like at the smaller scale. Begin with the core issue. In quantum field theory, forces are mediated by particles. The electromagnetic force is carried by photons. The strong force is carried by gluons. The weak force is carried by W and Z bosons. Each of these forces can be described by quantizing a classical field defined over space-time. If gravity is to be treated similarly, it should also have a quantum carrier particle. In weak field approximations, small ripples in space-time can be described as hypothetical particles called gravitons. These gravitons would be massless and spin 2, reflecting the tensor nature of the gravitational field. However, when physicists attempt to construct a quantum field theory of gravitons in the same way as other force carriers, calculations quickly produce infinities that cannot be controlled. Unlike quantum electrodynamics, where divergences can be renormalized, quantum gravity in this form is non-renormalizable. The coupling strength grows with energy in a way that makes the theory break down at high energies. String theory begins by changing the fundamental assumption. Instead of treating particles as point-like objects, string theory proposes that the basic constituents of nature are one-dimensional strings. These strings can vibrate in different modes. Each vibrational mode corresponds to a different particle. What we perceive as electrons, quarks, or photons are simply different excitation states of the same underlying string. This seemingly modest change has profound consequences. Because strings have finite length, typically assumed to be on the order of the Planck length, interactions are not localized at exact points. They are spread out over small but finite regions. This smearing effect softens the ultraviolet divergences that arise in point-particle quantum gravity. When the mathematics of string theory is worked out, something remarkable appears automatically. One of the vibrational modes of the string behaves exactly like a graviton. Gravity is not added by hand. It emerges as a necessary feature of the theory. In this sense, string theory provides a built-in quantum theory of gravity. However, consistency of string theory requires additional structure. The equations only work without anomalies in higher dimensional spacetimes. Most versions require 10 spatial dimensions plus 1 time dimension, or in certain formulations 11 dimensions in what is called M-theory. The extra dimensions are not directly observable because they are assumed to be compactified, curled up into extremely small shapes, possibly at scales near the Planck length. In string theory, the Planck length sets the characteristic scale at which strings operate. Distances shorter than the string length lose independent meaning because strings cannot probe structures smaller than their own extent. An important feature of string theory is T-duality. Under certain conditions, a universe compactified on a circle of radius r is physically equivalent to one compactified on a circle of radius 1 over r in appropriate units. This suggests that distances below a certain scale may be indistinguishable from larger distances. In some formulations, the string length acts as a minimum operational distance. Probing below that scale does not reveal new structure but instead maps back to physics at larger scales. This hints at a natural cutoff similar to the Planck length. String theory has also led to the holographic principle in a precise mathematical form through the ADS/CFT correspondence. This duality relates a gravitational theory in a higher dimensional space to a quantum field theory without gravity on its lower dimensional boundary. In such dual descriptions, spacetime geometry emerges from more fundamental quantum degrees of freedom. Loop quantum gravity takes a very different path. Instead of introducing new fundamental objects like strings, loop quantum gravity attempts to quantize spacetime directly. It starts with general relativity reformulated in terms of connection variables and then applies canonical quantization techniques. The result is that space itself becomes quantized. In loop quantum gravity, the geometry of space is described by spin networks. These networks consist of edges labelled by quantum numbers that determine discrete units of area, and nodes that determine discrete units of volume. Area and volume operators in this theory have discrete spectra. This means that there are smallest possible non-zero values for area and volume on the order of the Planck scale. Unlike string theory, loop quantum gravity does not require extra dimensions. It remains four-dimensional, but alters the microscopic structure of space. Time in loop quantum gravity is also treated differently. In some formulations, time does not appear as a fundamental parameter, but emerges from relations between quantum states of geometry. In cosmological applications, loop quantum gravity leads to models in which the Big Bang singularity is replaced by a quantum bounce. Instead of infinite density at zero volume, the universe reaches a minimum volume near the Planck scale and then expands. Despite their differences, both theories agree on one point. Classical smooth spacetime is not fundamental at arbitrarily small scales. In string theory, smooth geometry emerges from the collective behavior of strings. In loop quantum gravity, smooth geometry emerges from large networks of discrete quantum geometric elements. There are also other approaches, such as causal dynamical triangulations, asymptotic safety, and emergent gravity models. Each attempts to address the breakdown of classical spacetime at the Planck scale in a different way. None of these frameworks has yet been experimentally confirmed. One of the challenges is that their predictions often converge at low energies to reproduce classical general relativity and the standard model of particle physics. Distinguishing between them requires probing Planck scale physics directly or identifying subtle signatures that survive at accessible scales. Another challenge is mathematical consistency. String theory is highly constrained and mathematically rich, but it allows a vast landscape of possible solutions corresponding to different compactifications of extra dimensions. Selecting the solution that matches our universe remains an open problem. Loop quantum gravity is more conservative in retaining four-dimensional spacetime, but connecting it fully with the standard model of particle physics remains incomplete. The existence of these competing frameworks highlights the fact that the Planck scale is not merely a curiosity. It is the frontier where foundational questions converge. Are space and time fundamental, or do they emerge from deeper quantum structures? Are the building blocks of reality one-dimensional strings, combinatorial networks, or something else entirely? Is there truly a smallest unit of length, or does the Planck scale mark only a limit of current theoretical tools? Both string theory and loop quantum gravity treat the Planck length as a central parameter. In string theory, it is tied to the string scale. In loop quantum gravity, it determines the discrete spectra of geometric operators. In either case, LP is not just a small number. It defines the scale at which classical intuition fails and new principles must take over. Whether one of these theories, or an entirely different one, ultimately provides the correct description remains to be seen. What is certain is that any successful unification of quantum mechanics and general relativity must account for the Planck length and explain why it represents the boundary between smooth space-time and whatever deeper structure lies beneath it. When people first hear that the Planck length may represent the smallest meaningful distance in nature, a common mental image appears almost immediately. Space, they imagine, might be like a digital image. Zoom in far enough, and instead of smooth lines, you see pixels. Each pixel is a smallest unit. You cannot subdivide it further without losing information. The question then becomes direct. Does the Planck length represent a literal pixel of reality? It is an understandable analogy. Digital systems are familiar. Screens are made of pixels. Audio files are sampled at discrete intervals. The idea that the universe might be discretized at the smallest scales feels intuitive in a technological age. But the answer is more complicated than a simple yes or no. To begin, recall what the Planck length actually represents. It is derived from the constants h bar, g and c. It marks the scale at which quantum fluctuations of gravity become significant. It is the scale where attempting to localize energy more precisely leads to gravitational collapse. It is a boundary for meaningful measurement. None of that automatically implies that space is built from fixed cubic blocks of size 10 to the power of minus 35 meters. In classical geometry, space is continuous. Between any 2 points, there are infinitely many others. Calculus depends on that continuity. General relativity describes curvature using derivatives defined at arbitrarily small intervals. Quantum mechanics introduce discreteness into energy, angular momentum, and other quantities. But even quantum field theory is usually formulated on a continuous space-time background. The Planck length challenges that background assumption. If distances smaller than LP cannot be operationally distinguished because any attempt to measure them produces a black hole, then the concept of distance smaller than LP may not correspond to a physically meaningful question. That is different from saying space is made of fixed units of length LP. A useful comparison is the uncertainty principle. The uncertainty principle does not say that position and momentum come in discrete blocks. It says that their simultaneous precision is limited. There is a lower bound on the product of uncertainties, but position itself can still vary continuously within those bounds. Similarly, the Planck length may represent a lower bound on measurable distances without implying that space itself is composed of indivisible chunks. Some theories do propose discrete structure. In loop quantum gravity, area and volume operators have discrete spectra. This means that there are smallest possible non-zero eigenvalues for area and volume. In that framework, geometry has a quantized structure at the Planck scale. However, even in loop quantum gravity, the discrete units are not arranged in a regular grid like pixels on a screen. The structure is more abstract. Spin networks describe quantum states of geometry, and classical smooth space emerges only as an approximation when many such quanta are combined. The discreteness is relational rather than spatially uniform. In string theory, the situation is different. Strings have a characteristic length scale close to LP, but string theory does not necessarily replace continuous space-time with a discrete lattice. Instead, it suggests that distances shorter than the string length may not yield new independent physics. Through T-duality, certain compactified dimensions exhibit symmetry between large and small scales. A circle of radius r may be physically equivalent to a circle of radius 1 over r in appropriate units. This suggests that probing below a certain scale does not reveal finer detail in the usual sense. In this way, string theory also hints at a minimum operational scale without necessarily introducing discrete spatial pixels. Another angle to consider is information. Black hole entropy is proportional to area measured in units of LP squared. This implies that a region of space has a finite information capacity per unit area. If you try to pack more information into a region than allowed by this bound, gravitational collapse occurs. This supports the idea that space has a finite number of degrees of freedom per Planck area. If the number of degrees of freedom is finite in any finite region, then in some sense the structure is not infinitely detailed. There is a maximum density of information. That is consistent with the idea of a smallest meaningful unit of area or volume. But again, this does not require that space resembles a digital grid. Another important issue is symmetry. A simple lattice structure in space would break continuous rotational symmetry. If space were made of fixed cubes, physical laws might depend on direction at extremely small scales. Observations show no such directional dependence, even at very high energies. Any discrete structure must preserve Lorentz invariance and rotational symmetry at observable scales. This makes the notion of simple spatial pixels unlikely. Instead, if discreteness exists, it must be implemented in a way that preserves symmetry statistically or fundamentally. There is also the question of emergence. Some approaches to quantum gravity suggest that spacetime is not fundamental at all. Instead, it emerges from more basic quantum degrees of freedom, such as patterns of entanglement. In these models, asking whether space has pixels may be like asking whether temperature has pixels. Temperature is not a fundamental substance. It emerges from molecular motion. Similarly, geometry might emerge from deeper non-geometric variables. In such a scenario, the Planck length would mark the scale where the emergent description transitions from smooth to fundamentally quantum. Below that, distance might not even be the correct concept. This brings us back to operational meaning. To call LP a pixel implies that smaller distances do not exist in any sense. But physics rarely speaks in absolute metaphysical terms. It speaks in terms of measurable quantities. If no experiment can distinguish distances below LP, and if any attempt to do so results in gravitational collapse, then LP functions as the smallest operational unit of length. Whether there are sub-Planckian structures in some deeper theory that have no direct geometric interpretation remains an open question. There is also an important distinction between minimal measurable length and minimal coordinate separation. In classical mathematics, you can define coordinate differences smaller than any fixed number. In physical measurement, you cannot necessarily realize such coordinates. The Planck length may represent a lower bound on physically realizable distances, not necessarily on abstract coordinate values within a mathematical model. It is also possible that future theory will reinterpret LP differently. Some researchers have explored the idea of generalized uncertainty principles, where the standard Heisenberg relation is modified at high energies to include gravitational effects. In such formulations, there is an explicit minimal measurable length. These modifications arise from attempts to incorporate Planck-scale physics consistently into quantum mechanics. Still, no experimental evidence has yet confirmed such modifications. So does the Planck length mean reality has pixels? The cautious answer is that it suggests a limit to spatial resolution, and possibly a discrete structure of geometry, but not in the simple digital sense. It marks the scale where smooth spacetime ceases to be a reliable approximation. It may correspond to quantized units of area and volume in certain theories. It may represent the smallest operational distance that can be meaningfully defined. But whether reality is built from literal pixels, of length, LP remains uncertain. What is clear is that LP defines a boundary between classical intuition and quantum gravitational structure. It forces us to reconsider whether infinite divisibility of space is a physical truth or merely a mathematical convenience, and that naturally leads to deeper philosophical questions about whether space is fundamental at all, or whether it is something that emerges from a deeper layer of reality that does not resemble geometry in the way we currently understand it. For most of human history, space has been treated as the stage on which reality unfolds. Objects exist in space, events occur at locations, motion is defined as change of position in space over time. Even when scientific theories evolved, that basic picture seemed stable. Newton described absolute space as a fixed background. Einstein replaced it with dynamic space-time, but it was still the arena in which physical processes took place. The Planck scale challenges that assumption. If distances below 10 to the power of minus 35 meters cannot be operationally defined, and if geometry itself becomes subject to quantum uncertainty at that scale, then space may not be the fundamental layer of reality we once assumed it to be. To understand the philosophical weight of that statement, consider what it means for something to be fundamental. A fundamental entity does not arise from anything deeper. It is part of the basic ontology of the universe. If space is fundamental, then all physical objects and interactions exist within it. If space is not fundamental, then it must emerge from more primitive ingredients. General relativity already moved physics away from the idea of absolute space. In Einstein's framework, space-time is not a rigid container. It is shaped by matter and energy. Geometry responds to physical content. That shift blurred the line between stage and actors. Quantum gravity may blur it further. In several modern approaches, space-time is not assumed to exist at the most basic level. Instead, it appears as an emergent structure. In loop quantum gravity, the fundamental entities are not points in space but spin networks, combinatorial structures encoding quantum geometry. Space emerges as an approximation when these discrete elements are viewed collectively at scales much larger than the Planck length. In certain interpretations of string theory and holography, space-time geometry emerges from patterns of quantum entanglement in a lower dimensional theory. In these models, spatial distance between two regions may be related to the strength of entanglement between corresponding quantum degrees of freedom. If geometry depends on entanglement, then space is not primary, it is derived. This possibility represents a major conceptual shift. For centuries, geometry was treated as the most basic descriptive framework of reality. Euclidean geometry governed classical physics. Differential geometry governs general relativity. But if space emerges from non-geometric quantum relations, then geometry becomes secondary. There is also a historical philosophical debate that becomes relevant here. Isaac Newton argued for absolute space, a real, physical entity independent of objects. Gottfried Wilhelm Leibniz argued that space is relational, defined only by the relationships among objects. According to Leibniz, space does not exist independently of matter. Modern physics complicates both views. General relativity suggests that space-time has its own dynamical degrees of freedom, even in the absence of matter. Gravitational waves can propagate through vacuum. This seems to support a kind of substantivalism, the idea that space-time is something real. But if quantum gravity reveals that space-time emerges from deeper relations, the relational perspective gains new strength. In a relational view, the fundamental layer of reality consists of interactions, correlations, or algebraic structures. Spatial distance is not primary, but derived from patterns within that structure. The Planck length enters this philosophical discussion because it marks the scale where classical geometric notions cease to function independently. If space were truly fundamental and infinitely divisible, one would expect no lower bound to distance. The existence of a natural length scale suggests that geometry itself may have limits. Another philosophical implication concerns continuity. Continuity has been central to mathematics and physics for centuries. Calculus relies on smooth variation. Fields are defined at every point. Infinite divisibility is assumed. If space has a smallest meaningful scale, then continuity becomes an approximation rather than an absolute truth. That does not invalidate calculus. It simply means that calculus applies at scales much larger than LP, just as fluid mechanics applies at scales much larger than molecular spacing. The shift is conceptual. It suggests that smoothness is emergent. There is also the question of realism. Are Planck scale structures real in the same sense as atoms or stars? Or are they artifacts of our theoretical frameworks? Atoms were once theoretical constructs. Later, they were directly imaged and manipulated. The Planck length may remain forever beyond direct observation. Does that make it less real? In physics, reality is typically associated with measurable effects. The Planck length influences black hole entropy, cosmological singularities, and the unification of forces. Even if it cannot be measured directly, it shapes the consistency of our theories. In that sense, it has explanatory power, which is a strong indicator of physical significance. Another philosophical issue concerns infinity. Classical general relativity predicts singularities, infinities in curvature and density. Many physicists interpret these infinities as signs of theoretical breakdown rather than physical reality. The Planck scale provides a natural cutoff that prevents infinities from appearing in physically meaningful quantities. If quantum gravity replaces singularities with finite Planck scale structures, then infinities in spacetime are not real features of the universe. This supports a view in which nature avoids true mathematical infinities. There is also the matter of determinism. Quantum mechanics introduces fundamental indeterminacy. If spacetime geometry itself fluctuates at the Planck scale, then indeterminacy extends to the structure of space and time. Classical causality depends on well-defined light cones and metric structure. If geometry is uncertain at the smallest scales, then causality may be probabilistic at those scales as well. However, such fluctuations would average out at larger scales, preserving effective determinism in macroscopic phenomena. The Planck scale also forces reflection on the meaning of measurement. If distances smaller than LSP cannot be operationally distinguished, then asking whether such distances exist may be like asking about positions beyond the limits imposed by the uncertainty principle. Physics typically defines meaningful questions as those that can, in principle, be answered by experiment. If LP represents a fundamental limit, then space below that scale may not correspond to physically meaningful questions. This operational perspective aligns with a pragmatic view of scientific ontology. At the same time, some physicists argue that deeper mathematical structures may underlie even the Planck scale, even if they are not directly accessible. In that view, ELP marks a boundary for geometric description, but not necessarily for more abstract structures. Ultimately, the philosophical implications of the Planck length converge on one central issue: whether space is a basic ingredient of reality or a derived concept. If future theories confirm that geometry emerges from more primitive quantum relations, then space will join other concepts once thought fundamental, but later reinterpreted, like heat, which turned out to be molecular motion, or solidity, which turned out to be electromagnetic interaction. If, on the other hand, space retains some irreducible role even in quantum gravity, then LP may represent the smallest scale at which that fundamental structure manifests. In either case, the Planck length compels us to reconsider assumptions that once seemed unquestionable. Infinite divisibility, smooth continuity, absolute geometry. These may be approximations rather than ultimate truths. And when we step back from the mathematics and experiments, what remains is a universe in which the very fabric of distance and duration may arise from principles more subtle than classical geometry ever suggested. A universe where the smallest scale defines the boundary of our understanding, even as it shapes the structure of everything that appears at larger scales. We began with a simple question: is there a smallest possible distance that can exist? After moving from atom to quarks, from quantum uncertainty to gravitational collapse, from black holes to the early universe, the answer appears to be this. There is a scale at which our current understanding of space and time reaches its limit. That scale is the Planck length. Whether space is truly discrete at that scale, whether it emerges from deeper quantum relations, or whether LEP simply marks a boundary of measurement rather than an actual structural unit, the implication is the same. Infinite divisibility of space is not guaranteed by physics. It is a mathematical assumption that may not correspond to physical reality. That realization changes how we think about the universe. At everyday scales, space feels continuous. You can stretch a measuring tape across a room. You can draw a line and imagine dividing it without limit. Calculus works. Geometry works. Motion is smooth. Nothing in daily experience suggests a smallest unit of length. Even at atomic and nuclear scales, space behaves as though it is continuous. Quantum mechanics introduces uncertainty, but not a hard cutoff in position itself. The Planck scale lies so far below direct observation that it does not interfere with any practical measurement we perform, and yet, at the deepest theoretical level, the laws of physics converge toward a boundary. Gravity is weak, but it is universal. Quantum mechanics is subtle, but it is unavoidable. When these two frameworks intersect, they impose a limit. Try to probe too deeply, and you create a black hole. Try to confine too much energy in too small a region, and space-time responds dynamically. The Planck length is not just a number, it is a statement about the structure of physical law. It tells us that the geometry of the universe cannot be treated as infinitely fine. It tells us that space-time is not merely a passive stage but participates in quantum processes. It tells us that there are conditions under which our best theories must be replaced by something deeper. Living in a universe with a minimum meaningful length has consequences, even if they are not visible in daily life. It means that singularities predicted by classical theories are likely not physical infinities, but signs of incomplete descriptions. It means that the beginning of the universe was not a point of zero size, but a state governed by quantum geometry. It means that black holes do not compress matter into infinitely small points, but into configurations constrained by Planck scale physics. It also means that reality has a built-in scale of structure, even if that structure is not a literal grid or lattice. There is something striking about this conclusion. For centuries, physics advanced by discovering that phenomena once thought continuous were actually discrete. Matter is made of atoms, energy comes in quanta, electric charge is quantized, angular momentum is quantized. The Planck length extends that pattern to geometry itself. If space has a smallest meaningful unit of measurement, then geometry joins energy and matter in having a quantum aspect. This does not make the universe simpler, it makes it more layered. At macroscopic scales, classical geometry works perfectly. At atomic scales, quantum mechanics dominates, but space remains effectively smooth. At Planck scales, geometry and quantum mechanics intertwine. What is especially remarkable is how this smallest scale is defined. It is not introduced by hand. It emerges inevitably from the constants that govern light, gravity, and quantum action. Combine h-bar, g, and c, and LP appears. That combination is not arbitrary. It reflects the structure of the laws themselves. The fact that three independent constants produce a natural length suggests that the Planck scale is woven into the architecture of the universe. It also reminds us of how incomplete our understanding remains. We do not yet possess a confirmed theory of quantum gravity. String theory, loop quantum gravity, and other approaches offer competing frameworks. Each attempts to describe what happens when spacetime becomes quantum. None has been experimentally verified. The Planck length therefore stands at the frontier between known physics and unknown physics. It is the boundary beyond which our equations lose predictive power. It is the scale at which classical geometry dissolves into quantum uncertainty. It is the threshold of the earliest moment in cosmic history and the innermost structure of black holes. And yet, it is also unimaginably small compared to anything we can directly access. That contrast is part of what makes it so compelling. We live at scales many orders of magnitude larger than LP. The air we breathe, the ground we stand on, the stars we observe, all are governed by effective laws that average over Planck scale details. The smallest meaningful distance does not constrain how we build houses or measure planets. It shapes only the deepest layer of the physical framework. Still, its existence alters our philosophical perspective. If there is a smaller scale, then the infinite divisibility assumed in classical thought is not a physical truth. It is an approximation. The universe has a built-in grain, even if that grain is invisible to us. It suggests that reality may be finite in resolution, even if vast in extent. And perhaps most importantly, it shows that the search for understanding does not end with smaller and smaller pieces of matter. Eventually, the question shifts from what is it made of to what makes distance itself possible. The Planck length represents that shift. It marks the scale where matter, energy, geometry, and information converge. It marks the point where measurement encounters its own boundary. It marks the place where classical intuition must give way to quantum gravity. We may never measure LP directly. We may never observe a Planck scale fluctuation. But the requirement that such a scale exists is embedded in the consistency of our most successful theories. Living in a universe with a minimum meaningful size does not make the cosmos smaller. It makes it deeper. It means that beneath every meter, every nanometer, every femtometer, there is a limit, a threshold where the familiar dissolves and new principles take over. And while we may not yet fully understand those principles, the existence of that boundary continues to guide the search for a unified description of reality, reminding us that even in a universe governed by vast distances and cosmic expansion, the smallest scale carries some of the most profound implications.